Two objects the size of Manhattan, each one heavier than the sun, spiraling toward each other for 1 billion years. And when they finally touch, the collision lasts less than a second. In that single moment, more energy is released than every star in the Milky Way combined. The ground beneath reality itself begins to shake. And somewhere in that cataclysmic fireball, every atom of gold that has ever existed, including the ring on your finger and the metal in your phone, is being born. This is a neutron star merger, the most violent event in the known universe since the Big Bang itself. And for decades, it was purely theoretical. Scientists could predict the physics, write the equations, model the shock waves, but they had never seen one. They had never caught the moment of impact. Until August 17th, 2017. On that morning, 3 gravitational wave detectors on opposite sides of the planet felt a ripple pass through spacetime. A distortion so faint it moved each detector less than 1,000th the width of a proton. And then, 1.7 seconds later, a gamma-ray burst arrived. Telescopes around the world swiveled toward a single point in the sky, and what they saw rewrote the astronomy textbooks overnight. A fireball glowing with the light of 200 million suns, jets of matter screaming outward at 99.9% the speed of light, and a glowing cloud of freshly minted elements, still radioactive, still hot, expanding into the dark. It was the first time in human history we watched the universe create something precious out of death, and the deeper we looked, the stranger it became. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The largest stars in the universe are living on borrowed time from the moment they ignite. They burn bright, hotter than anything you can imagine, fusing hydrogen into helium at a ferocious rate that smaller stars would never dare attempt. And they do it knowing full well that the bigger the fire, the faster the fuel runs out. A star like our Sun will burn steadily for about 10 billion years before it runs into trouble. These monsters, the ones weighing 20, 30, 50 times what our Sun weighs, they get maybe 10 million years, a cosmic blink. They are born enormous and doomed, and everything that happens afterward is just gravity waiting for its moment. For most of their short lives, these massive stars sit on what astronomers call the main sequence. That's the long stable period where a star is fusing hydrogen in its core, and the energy from that fusion pushes outward hard enough to balance the crushing weight of all the layers above, trying to collapse inward. It's a tug of war, pressure versus gravity. As long as the core has hydrogen to burn, the star holds the line. But hydrogen doesn't last forever. And when it runs out, the core contracts. Temperature spikes. The star starts fusing helium into carbon and oxygen. The outer layers, no longer supported by the same fury of energy from below, begin to expand outward. The star swells into a red supergiant, a bloated dying thing that can grow large enough to swallow planets. Inside that swollen shell, the core keeps contracting, keeps heating, keeps fusing heavier and heavier elements, carbon into neon, neon into magnesium, oxygen into silicon, silicon into iron. Each stage burns faster than the one before it. Hydrogen fusion can run for millions of years. Silicon fusion lasts about a day, and then the core is made of iron, and that is where the story ends. Iron is the breaking point. Fusing iron doesn't release energy, it costs energy. The moment a massive star's core turns to iron, the outward pressure stops. There is nothing left to hold the weight, and gravity, which has been waiting patiently for tens of millions of years, finally wins. The collapse happens faster than a human brain can process the idea of speed. The core, roughly the size of Earth and containing more mass than our Sun, implodes in less than a second. Electrons get crushed into protons, forming neutrons and releasing a flood of neutrinos that carry away most of the energy. The outer layers, no longer supported, fall inward at a quarter of the speed of light and slam into the now rigid neutron core. The rebound is catastrophic. The star explodes. We call it a core collapse supernova, and for a few weeks that single dying star can shine brighter than an entire galaxy of hundreds of billions of stars. The explosion ejects the outer layers into space, scattering the elements forged in the core across light years of surrounding gas. Everything heavier than hydrogen and helium in your body, in the ground beneath your feet, in the device you're watching this on, came from a supernova. You are made of star guts, but the core doesn't explode, the core survives. What's left after the outer layers are blown away is a ball of neutrons held together by gravity and supported only by something called neutron degeneracy pressure. This is not normal pressure the way you experience it when you squeeze a balloon. This is quantum mechanical resistance, the universe's refusal to let certain particles occupy the same space in the same state. Pack neutrons tightly enough and they push back. Not because they want to, but because the laws of physics say they have to. That resistance is the only thing standing between a neutron star and total gravitational collapse into a black hole. The result is an object so dense that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. The entire mass of our Sun, compressed into a sphere roughly the size of a city. Manhattan would fit comfortably across its diameter. Some neutron stars are smaller. The density is beyond comprehension. If you could somehow stand on the surface of a neutron star, and you can't because you would be crushed into a smear of atomic nuclei before you got within 1,000 kilometers. But if you could, gravity would be so strong that it would flatten you into a layer 1 atom thick in a fraction of a millisecond. Mountains on a neutron star are measured in millimeters because gravity won't allow anything taller. And they spin. When the core collapses, it conserves angular momentum. A star that was rotating slowly over a diameter of millions of kilometers suddenly finds all that rotational energy packed into an object 20 kilometers across. The spin rate skyrockets. Some neutron stars rotate hundreds of times per second. The fastest known, the millisecond pulsars, are spinning so fast that their surfaces are moving at a significant fraction of the speed of light. A point on the equator of one of these objects is traveling at something like 50,000 kilometers per second. If you were standing on that surface, which again you are not because you are dead, the horizon would be rising and falling hundreds of times every second. The sky would blur into a smear. Then there are the magnetic fields. Neutron stars inherit the magnetic field of their parent star, and when you compress that field down into a city-sized object, the strength goes up by a factor of trillions. Earth's magnetic field measures about half a gas at the surface. A typical neutron star clocks in at 1 trillion gas. Some, the magnetars, reach 10 to the 15th gas. At that strength, the magnetic field itself warps the structure of empty space. Atoms stretched into thin rods. Chemistry stops working the way it should. If you brought a magnetar within 1,000 kilometers of Earth, and this is a thought experiment because it would also tidally shred the planet, but if you did, it would erase every piece of magnetic storage on the surface. Credit cards, hard drives, MRI machines, all of it gone. The field is strong enough to pull the iron out of your blood, but you wouldn't live long enough to notice because the tidal forces would have already disassembled you at the molecular level. Now, most neutron stars are born alone. Their companion star, if they had one, was either blown away during the supernova or wasn't massive enough to go supernova itself and just drifted off as a white dwarf or a smaller remnant. But some, a small fraction, are born in binary systems, two massive stars orbiting each other. Both go supernova, both leave neutron stars behind. And if the system survives both explosions without being torn apart, what you're left with is two of the densest objects in the universe locked in orbit around a shared center of mass, circling each other at speeds that start off relatively sedate and then, over time, get faster. This is where Einstein enters the conversation. According to general relativity, any two masses orbiting each other produce gravitational waves, ripples in the fabric of spacetime itself, radiating outward at the speed of light. These waves carry energy, not much, but enough. And as the system loses energy to gravitational radiation, the orbit shrinks. The two neutron stars spiral inward, slowly at first, then faster. This is not a quick process. For a binary neutron star system born with a relatively wide orbit, the inspiral can take hundreds of millions of years. In some cases, billions. The stars circle each other for eons, invisible, silent, locked in a dance that has only one possible ending. Astronomers have measured this process directly. There is a binary pulsar system, two neutron stars orbiting each other every few hours, and over decades of observation, scientists have clocked the rate at which the orbital period is shrinking. The measurement is absurdly precise. The orbit is decaying by roughly 2/trillionths of a second per second. That number matches the prediction from general relativity so exactly that it earned the discoverers a Nobel Prize. The system is losing energy to gravitational waves, and the waves are real, and the orbit is collapsing, and in about 300 million years those two stars are going to merge. 300 million years sounds like forever. It isn't. On cosmic timescales, it's a countdown, and there are systems out there with much shorter fuses. Binaries that are closer, tighter, already deep into the final stages of the inspiral. Some have only a few 100,000 years left. A few have less. Somewhere in the universe right now, there is a binary neutron star system that has minutes remaining before collision, and the gravitational waves it is producing are screaming across space, stretching and compressing every bit of matter they pass through by amounts smaller than the width of a proton. We wouldn't feel it, we wouldn't hear it. But if we had the right instruments pointed in the right direction at the right time, we could detect it. As the orbit tightens, the process accelerates. Closer orbit means faster orbital speed. Faster speed means stronger gravitational waves. Stronger waves mean more energy loss. More energy loss means the orbit shrinks faster. It's a runaway. For most of the billions of years these systems exist, the inspiral is glacial. Then, in the final hours, it becomes violent. The two neutron stars, each one a ball of matter so dense that a cubic centimeter outweighs an aircraft carrier, begin whipping around each other hundreds of times per second. The gravitational waves pouring off the system grow louder, stronger, until they are shaking space-time itself hard enough to be heard across the universe. The final plunge, the part where the stars are close enough that their surfaces are beginning to deform under each other's tidal pull, lasts only minutes. For a neutron star binary, that final detectable inspiral before merger, the part where the gravitational wave frequency sweeps into the range that instruments like LIGO can hear, runs for something like 6 minutes. 6 minutes of slowly rising pitch, a cosmic chirp that starts low and climbs higher and higher as the stars accelerate toward each other, until at the very end the signal cuts off. That cutoff is the merger. The moment two dead stars, remnants of supernovae that exploded millions or billions of years ago, finally touch. Everything up to this point has been slow. Stellar evolution takes millions of years. The inspiral takes hundreds of millions more. Even the final audible chirp, the part humans can detect with gravitational wave observatories, lasts minutes. But the collision itself is instantaneous. Two objects, each containing more than the mass of the Sun, each spinning hundreds of times per second, slam into each other at a significant fraction of the speed of light. The impact releases more energy in a single second than our Sun will produce in its entire 10 billion-year lifetime. For one brief moment, the collision site becomes one of the brightest objects in the universe. And that collision, that moment of cosmic violence, is not the end of the story. It is the beginning of something stranger. Because when neutron stars merge, they don't just destroy each other. They create. The temperatures and pressures during the collision are so extreme that atomic nuclei are no longer stable. Protons and neutrons are free-floating, smashing together, building heavier and heavier elements in a process that cannot happen anywhere else in the universe. The heaviest elements on the periodic table, the ones that are too massive to be forged inside even the largest stars, are made here. In the crushing chaos of two neutron stars tearing each other apart, the universe manufactures gold, platinum, uranium. Everything heavier than iron that isn't made in a supernova gets made here, in collisions so rare and so violent that for a long time we could only guess they were happening at all. We don't have to guess anymore. On August 17, 2017, gravitational wave detectors on two continents picked up a signal. It was different from the black hole mergers that had been detected before. Longer, softer. The chirp lasted over a minute, rising slowly in frequency, exactly the way a neutron star in spiral should sound. Less than 2 seconds after the gravitational wave signal ended, a gamma-ray telescope in orbit detected a short burst of high-energy light from the same patch of sky. Then, over the following hours and days, dozens of other telescopes all over the world and in space turned to look. They found a glowing cloud of debris, cooling and fading, radiating light across the spectrum. Visible light, infrared, ultraviolet, X-rays, radio, every wavelength we know how to detect lit up with the afterglow of something that had just torn itself apart. The event had happened 130 million years ago, back when dinosaurs were still walking on Earth. The light and the gravitational waves had been traveling toward us ever since, crossing the gap at the speed of light, carrying the news of a collision that reshaped a small corner of the universe. By the time it reached us, the signal had stretched and faded, but it was still strong enough to read, strong enough to measure, strong enough to confirm that neutron star mergers are real, that they produce the elements we see in our own solar system, and that the universe has been running this process over and over for billions of years. Every gold ring, every platinum catalyst, every uranium fuel rod, all of it came from events like this one, forged in collisions between the corpses of dead stars. This is what leads to those collisions. Stars that lived fast and died violently. Cores that survived their own destruction and collapsed into objects dense enough to bend spacetime. Binary systems that held together through two supernovae and then spent hundreds of millions of years slowly, inexorably falling toward each other. And at the end of that fall, a collision so energetic that it briefly rivals the brightness of an entire galaxy. That is the machinery. That is how the universe builds the heaviest elements. Not in the cores of stars, not in supernova explosions, in the final seconds of a dance between two objects that should not exist, spinning around each other faster and faster, until there is nowhere left to go but into each other, and we are just beginning to understand what happens next. Einstein did not set out to discover gravitational waves. He was trying to solve a completely different problem, one that had been bothering physicists since the late 1800s. The problem was gravity itself. Isaac Newton had given the world a beautiful equation for how gravity works. Two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. It worked. It predicted planetary orbits. It explained tides. It let you calculate the trajectory of a cannonball. But it had a flaw that Newton himself admitted he could not explain. The force, according to his equation, acted instantaneously across any distance. Move the sun, and Earth would feel it immediately, even though the sun is 93 million miles away. That bothered people. It bothered Einstein especially, because by 1905 he had already worked out special relativity, which said very clearly that nothing, no information, no force, no signal of any kind can travel faster than the speed of light. Instant action at a distance violated that rule. Gravity needed a speed limit, so Einstein spent the next decade rebuilding gravity from the ground up. What he came up with in 1915 was general relativity, and it was not just an improvement on Newton, it was a completely different way of thinking about what gravity is. Newton had treated gravity as a force, something that reached across empty space and pulled. Einstein said no, gravity is not a force. Gravity is geometry. Mass and energy do not pull on other objects. They warp the shape of space and time itself, and objects moving through that warped space-time follow curved paths. A planet does not orbit the sun because the sun is pulling it. The planet orbits because the sun has bent space-time into a shape where the straightest possible path, what we call a geodesic, happens to be an ellipse. You are not being pulled toward the center of the Earth right now. You are trying to follow a straight line through space-time, and the Earth has curved space-time so severely beneath you that your straight line aims downward. The ground is in your way. That is why you feel weight. You are being blocked from falling. It is a strange picture. Space-time, in Einstein's model, is not a backdrop. It is not a stage where events happen. It is a physical thing, a fabric that can stretch and bend and ripple. And if masses can curve space-time just by sitting there, what happens when masses move? Einstein worked through the math and found that accelerating masses changing speed or direction, should send ripples outward through space-time itself. He called them gravitational waves. They would travel at the speed of light, stretching and squeezing space as they passed, and they would carry energy away from whatever system produced them. The prediction was published in 1916, tucked into a paper on the broader framework of general relativity. It was a footnote to a revolution. For decades, almost nobody took gravitational waves seriously. The reason was simple. The effect was absurdly small. Einstein himself calculated that even the most violent events he could imagine, stars orbiting each other, collapsing objects, exploding suns, would produce ripples so faint that detecting them would be effectively impossible. He was not being pessimistic. He was being accurate. A gravitational wave passing through Earth does not knock things over. It does not shake buildings. It does not even move dust. What it does is change distances. As the wave passes, space itself stretches in one direction and compresses in the perpendicular direction, then reverses. The effect is rhythmic, oscillating at whatever frequency the source is vibrating. But the amount of stretch is tiny beyond comprehension. Take two objects a kilometer apart and let a strong gravitational wave, the kind produced by merging black holes a billion light-years away, pass between them. The distance between those objects will change by about 1/10,000th the width of a proton. That is the signal. That is what you have to measure if you want to detect a gravitational wave directly. To put that in perspective, if you wanted to measure a change that small using a ruler the size of the distance from Earth to the nearest star, you would need to detect a shift smaller than the width of a human hair. Except worse, because your ruler is also made of atoms, and those atoms are jiggling from heat, and the ground beneath you is trembling from seismic noise, and trucks are driving past, and the wind is blowing, and someone 3 states over just slammed a door. Every one of those vibrations is millions of times larger than the signal you are trying to find. For most of the 20th century, the consensus was that gravitational waves were real in theory but undetectable in practice, a beautiful prediction that would never be tested. Then in 1974, 2 astronomers at the University of Massachusetts, Russell Hulse and Joseph Taylor, were using the Arecibo radio telescope in Puerto Rico to search for pulsars. Pulsars are rotating neutron stars that emit beams of radio waves from their magnetic poles. As the star spins, the beam sweeps across space like a lighthouse, and if Earth happens to be in the path, we see a pulse. Some pulses are extraordinarily regular, ticking away with a precision that rivals atomic clocks. Hulse and Taylor found one, catalogued as PSR 1913+16, that was different. Its pulses were not steady, they were shifting, speeding up and slowing down in a regular pattern that repeated every 7.75 hours. The only explanation that fit was that the pulsar was not alone. It was in orbit around another neutron star, and as it moved toward and away from Earth during each orbit, the radio pulses were Doppler shifted. The timing pattern let them work out the orbit in extraordinary detail. 2 neutron stars, each roughly 1.4 times the mass of the Sun, circling each other every 7.75 hours, at an average separation of about 3 times the Earth-Moon distance. Once they had the orbit, they could do something much more interesting. They could watch it change. General relativity predicted that a system like this should be radiating gravitational waves, losing energy, and as a result, the orbit should be shrinking. The orbital period should be decreasing over time, and the rate of that decrease should be calculable. Taylor and his colleagues measured the pulsar's timing for years, tracking how the orbit evolved. The orbital period was shrinking by about 76 microseconds per year. They compared that number to the prediction from general relativity. The match was exact to within 0.5%. The gravitational waves were real. The energy was leaving the system at precisely the rate Einstein's equations said it should. It was the first indirect proof that gravitational waves exist, and it earned Hulse and Taylor the Nobel Prize in 1993. But it was still indirect. The waves themselves had not been detected. Nobody had felt space-time ripple. Building a detector that could feel space-time ripple required rethinking what a detector even is. You cannot build a gravitational wave detector the way you build a telescope. A telescope collects light. Light interacts with matter. Photons hit a mirror, they bounce. They hit a detector, they get absorbed. Gravitational waves do not interact with matter in that sense. They are distortions in the geometry of space itself. You cannot catch them. You cannot block them. You can only measure what they do to the space you are sitting in, and what they do is change distances. So the detector has to be something that measures distance with absurd precision. The tool that does this is called an interferometer. An interferometer works by splitting a beam of light into 2 paths, sending those beams down 2 perpendicular arms, bouncing them off mirrors at the ends, and bringing them back together. When the beams recombine, they interfere with each other. If the 2 arms are exactly the same length, the light waves line up perfectly and you get a bright spot. If one arm is even slightly longer than the other, The waves arrive out of phase and they cancel, producing darkness. The amount of brightness or darkness tells you, with extraordinary sensitivity, how much the arm lengths differ. If a gravitational wave passes through the detector, it will stretch one arm and compress the other. The light traveling down the stretched arm takes slightly longer to return. The light in the compressed arm returns slightly sooner. When they recombine, the interference pattern shifts. That shift is the signal. The first serious attempts to build gravitational wave detectors using this principle started in the 1960s and 70s. Early interferometers were small, a few meters on a side, and they detected nothing. The arms were too short. The mirrors were not isolated well enough from vibrations. The lasers were not stable. It became clear that if you wanted to detect gravitational waves, you needed to go big, really big. The longer the arms, the larger the distance change caused by a passing wave, and the easier it is to measure. By the early 1990s, the physics community had convinced the United States government to fund the Laser Interferometer Gravitational Wave Observatory, LIGO. 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by 3,000 kilometers. Each detector would have arms 4 kilometers long, 2.5 miles. The longest laser beams ever built for a scientific instrument. LIGO was not just big, it was preposterously sensitive. The mirrors at the ends of the arms, each weighing 40 kilograms and made from ultra-pure glass, were suspended by thin wires and isolated from ground vibrations by multi-stage suspension systems. The laser light bounced back and forth inside the arms hundreds of times before recombining, effectively increasing the arm length and amplifying the signal. The entire apparatus sat inside a vacuum tube to eliminate air currents and pressure fluctuations. Every component was designed to reduce noise, seismic vibrations from earthquakes halfway around the world, thermal noise from the random jiggling of atoms in the mirrors, quantum noise from the uncertainty principle affecting individual photons. All of it had to be pushed below the level of the signal LIGO was hunting. Initial LIGO, the first version, ran from 2002 until 2010. It detected nothing, not a single confirmed gravitational wave. That was not a failure. The instrument had been built at the edge of what was technically possible, and the sensitivity was exactly what the engineers had promised. It just was not quite sensitive enough to catch the waves that were out there. Theoretical predictions said that to reliably detect gravitational waves from merging black holes or neutron stars, LIGO needed to be about 10 times more sensitive. So they shut it down and spent 5 years upgrading it. Advanced LIGO came online in September 2015 with better lasers, better mirrors, better seismic isolation, and better everything. The sensitivity was now high enough that the detectors could hear black hole mergers out to a distance of more than 1 billion light-years. The upgrade worked. 4 days after advanced LIGO turned on, it detected a signal. That first detection, announced publicly in February 2016, was from 2 black holes merging, not neutron stars, but it proved the concept. Gravitational waves were no longer theoretical. They were measurable. The signal, labeled GW150914 for the date it arrived, showed exactly the pattern predicted by general relativity. A chirp, a rising tone that started low and climbed higher and higher as the 2 black holes spiraled inward, accelerating as they fell toward each other. The frequency swept upward over a fraction of a second, then cut off abruptly at the moment of merger. The black holes, weighing about 36 and 29 times the mass of the Sun, had combined into a single black hole of 62 solar masses. 3 solar masses, the difference, had been converted entirely into gravitational wave energy and radiated outward into space. For a brief moment, that collision had released more power than all the stars in the observable universe combined, and LIGO had heard it. Not light, not radio waves, not particles, just the ringing of space-time itself. The discovery earned the Nobel Prize in 2017. The announcement called it one of the most important advances in physics in decades. Rainer Weiss, one of the founders of LIGO, said in his Nobel lecture that they had heard the sound of space-time. Kip Thorne, the theoretical physicist who had spent 40 years predicting what gravitational wave signals should look like, said it was the first time humanity had been able to hear the universe. Because that is what gravitational wave astronomy is. It is not looking, it is listening. Light can be blocked by dust, absorbed by gas, scattered by electrons. Gravitational waves pass through everything. They travel across the universe unimpeded, carrying information from regions that are completely dark to traditional telescopes. A black hole merger happens in total darkness. No light escapes. But the gravitational waves pour out, carrying the story of what happened, encoded in their frequency and amplitude. Neutron star mergers produce a different kind of signal. Black holes are smooth. They have no surface, no structure, just an event horizon and empty space. When two black holes merge, the gravitational wave signal is clean. A chirp that rises smoothly in frequency, a brief ringdown as the merged object settles into its final shape, and then silence. Neutron stars are messier. They have surfaces. They have interiors with structure, layers of different densities, maybe solid crusts, maybe exotic states of matter in their cores that we have never seen in a laboratory. When two neutron stars spiral toward each other, they start emitting gravitational waves the same way black holes do. A rising chirp, but as they get closer, tidal forces start to deform them. Each star raises a tidal bulge on the other, the way the moon raises tides on Earth's oceans, except these tides are being raised on objects made of neutrons held together by degeneracy pressure. The bulges carry extra mass, and that extra mass changes the gravitational wave signal in subtle ways. The frequency does not rise as smoothly. There are tiny deviations, wiggles in the waveform that encode information about how stiff the neutron star material is, how much it resists being squeezed. As the stars get even closer, the tidal forces grow stronger. At some point, the stars are so close that they are literally touching, their outer layers beginning to merge while their cores are still intact. The gravitational wave signal becomes chaotic. The two objects are no longer separate. They are a single writhing mass of neutrons, spinning hundreds of times per second, radiating furiously. Then, depending on the total mass, one of two things happens. If the combined mass is below a certain threshold, the merged object might survive as a single massive neutron star, a hypermassive neutron star held up temporarily by rapid rotation and thermal pressure. It will radiate gravitational waves as it spins down and eventually collapse into a black hole seconds or minutes later. If the combined mass is above the threshold, the collapse is immediate. The object goes straight to black hole without passing through any intermediate stage. Either way, the gravitational wave signal cuts off. The ringdown is brief, and what you are left with is silence, at least in gravitational waves. But the signal does not stop there, because unlike black hole mergers, neutron star mergers produce light, a lot of light. The collision ejects material, hot neutron-rich matter flung outward at a significant fraction of the speed of light. That material is radioactive. It is packed with unstable, heavy nuclei that decay rapidly, releasing energy. The cloud glows, cooling and fading over hours and days, but bright enough to be seen across hundreds of millions of light years with ordinary telescopes. Astronomers had predicted this. They called it a kilonova, and they had models for what it should look like. But nobody had ever seen one, because to see a kilonova, you first need to know where and when the neutron stars are going to merge. You need an early warning. You need gravitational waves. LIGO and its partner detectors, Virgo in Italy, had joined the network by 2017, were scanning the sky constantly, listening for the chirp. They were hearing black hole mergers regularly by mid-2017, one every few weeks. The catalogue was growing. But neutron stars are smaller, lighter, and their mergers produce weaker gravitational waves that do not carry as far. The detection rate was expected to be lower. Still, the instruments were sensitive enough now that a neutron star merger within a few 100 million light-years should be loud and clear. It was just a matter of time. On August 17, 2017, at 12:41 UTC, both LIGO detectors, Hanford and Livingston, registered a signal. It was different from the black hole chirps they had been seeing. It was longer, lasting over a minute instead of a fraction of a second. The frequency started lower and climbed more slowly. The shape of the waveform matched the theoretical predictions for a binary neutron star in spiral. Virgo, the detector in Italy, saw something too, but the signal was weak, which was useful because it meant the source was probably located in a part of the sky where Virgo's antenna pattern was least sensitive. By combining the data from all three detectors, the LIGO-Virgo collaboration was able to narrow the source down to a patch of sky roughly 30 square degrees, about 150 times the area of the full moon. That is huge by astronomical standards, but it was small enough to search. Alerts went out immediately to telescopes all over the world. Something had just merged, and if the models were right, there should be light. Less than 2 seconds after the gravitational wave signal ended, NASA's Fermi Gamma-Ray Space Telescope detected a short gamma-ray burst from the same region of the sky. Gamma-ray bursts are among the most energetic explosions in the universe, brief flashes of high-energy light that last anywhere from milliseconds to a few minutes. Astronomers had long suspected that at least some gamma-ray bursts were caused by neutron star mergers, but the evidence had always been circumstantial. Now, for the first time, there was a direct connection. Gravitational waves and gamma rays arriving within seconds of each other from the same event 130 million light-years away. The light had been traveling toward Earth since the late Cretaceous, back when Tyrannosaurus rex was walking around, and it had finally arrived carrying the news of a collision that had reshaped a corner of space in a galaxy we had barely paid attention to until that moment. The gamma-ray burst told telescopes where to look. Within hours, optical telescopes in Chile picked up a new point of light in a galaxy called NGC 4993, a lenticular galaxy in the constellation Hydra. The light was bright blue at first, then fading and reddening over the following days. Other telescopes joined in: Hubble, Spitzer, Chandra, radio dishes. Every instrument that could point at that patch of sky did. For the first time in history, a single cosmic event had been observed in gravitational waves, gamma rays, visible light, infrared, ultraviolet, X-rays, and radio. It was the birth of multi-messenger astronomy, the ability to watch the universe using every messenger particle and wave we know how to detect: photons, neutrinos, and now gravitational waves. The universe was no longer something we just looked at. It was something we could listen to and feel. The detection of GW 170817, the label assigned to that neutron star merger, changed astronomy in ways that are still unfolding. But before we get to what the telescopes saw, before we talk about the Kilonova and the gamma rays and the jets and the gold, we need to understand what happened in those final moments. What happens when two neutron stars collide at 99.9% the speed of light? On August 17th, 2017, at 12:41 Coordinated Universal Time, something happened that had never happened before in the history of science. Two entirely different observatories, using two completely different branches of physics, detected the same cosmic event at almost exactly the same moment. One observatory heard spacetime ringing. The other saw a flash of gamma rays. Neither instrument had any business detecting the same thing, and yet there they were, two independent signals arriving within 2 seconds of each other from the same patch of sky 130 million light-years away. For astronomers, this was not just a discovery, it was the opening of a door that most of them had spent their entire careers assuming would stay locked. The first signal came from LIGO, the Laser Interferometer Gravitational Wave Observatory. Two detectors, one in Hanford, Washington and one in Livingston, Louisiana, each with arms stretching 4 kilometers into the scrubland, had been listening to the universe for gravitational waves since advanced LIGO came online in September 2015. By mid-2017, they had heard about a dozen black hole mergers. The catalog was growing. Each detection was extraordinary in its own right, proof that Einstein's predictions were real and that humanity could now eavesdrop on the most violent events in the cosmos. But all of those earlier signals had come from black holes, dense, dark, silent objects that swallow everything, including light. When black holes merge, the only thing that escapes is the gravitational wave signal itself. There is no flash, no glow, no electromagnetic signature of any kind. You hear them with gravitational wave detectors, or you do not detect them at all. Neutron stars are different. Neutron stars have surfaces, they have matter, and when neutron stars collide, that matter does not vanish quietly into an event horizon. It explodes outward in a spray of superheated debris, moving at a significant fraction of the speed of light. Theorists had been predicting for decades that neutron-star mergers should produce electromagnetic signals, flashes of light across multiple wavelengths, gamma rays, X-rays, visible light, infrared, radio, a whole fireworks display. But predictions are cheap. Nobody had ever seen one. Because to see the light from a neutron-star merger, you first need to know when and where the merger is happening. You need advance notice, you need gravitational waves. LIGO's data pipeline is automated. When a candidate signal shows up in the data stream, the software flags it, runs a series of checks to determine whether it is real or just noise, and if the signal passes those checks, it sends out an alert. Automated, immediate. No humans in the loop for the first few seconds. At 12:41 UTC, the pipeline flagged a signal that looked different from the black hole mergers the detectors had been seeing. The waveform started at a lower frequency and lasted much longer. Over a full minute of rising tone, a slow, steady chirp that climbed from about 24 Hz up to several hundred Hz before cutting off abruptly. The shape matched the theoretical prediction for a binary neutron star in spiral almost perfectly. Two objects, each weighing roughly 1.4 times the mass of the Sun, spiraling toward each other, accelerating as they lost energy to gravitational waves, and finally merging. Virgo, the European gravitational wave detector located near Pisa, Italy, had joined the observing run just 2 weeks earlier. Virgo saw the signal too, but much more weakly. That weakness was useful. It meant the source was likely located in a part of the sky where Virgo's antenna pattern, the directional sensitivity of the detector, was least responsive. Gravitational wave detectors are not like optical telescopes. You cannot point them. They are sensitive to the entire sky at once, but the sensitivity varies depending on direction. By combining the timing and amplitude data from all three detectors, LIGO and Virgo, the collaboration could triangulate the source. The result was a patch of sky roughly 30 square degrees in size. For context, the full moon covers about half a square degree. 30 square degrees is 60 full moons laid side by side. A huge area by the standards of optical astronomy, but small enough to search. Alerts went out within minutes to observatories all over the world. Something had just merged, and if the models were right, there should be light arriving soon. Less than 2 seconds after the gravitational wave signal ended, NASA's Fermi Gamma Ray Space Telescope detected a short burst of high-energy gamma rays. The burst lasted about 2 seconds and came from the same general region of the sky that LIGO and Virgo had identified. The detection was flagged automatically and reported through the Gamma Ray Coordinates Network, a system that distributes alerts about transient gamma-ray sources to astronomers in real time. Moments later, the European Space Agency's Integral satellite confirmed the detection. 2 independent gamma-ray observatories had seen the same flash within seconds of the gravitational wave signal. The connection was immediate. This was not a coincidence. The neutron stars had not just merged, they had exploded. Short gamma-ray bursts, the kind lasting less than a few seconds, had been one of astronomy's persistent mysteries since their discovery in the late 1960s. They appeared randomly across the sky, flashed once and vanished. For decades, nobody knew what caused them. The leading theory developed in the 1990s was that they were the result of neutron-star mergers. The idea made sense. Merge 2 neutron stars, and the collision should produce a pair of relativistic jets, narrow beams of matter and radiation moving at close to the speed of light, blasted outward along the rotation axis of the merged object. If one of those jets happened to point toward Earth, you would see a brief, intense flash of gamma rays, a short gamma-ray burst, but the theory had never been proven. Nobody had ever caught a neutron-star merger and a gamma-ray burst at the same time. Until now. The coincidence, gravitational waves and gamma rays arriving within 2 seconds of each other from the same patch of sky, was so statistically unlikely to be random that it effectively confirmed the connection on the spot. Neutron-star mergers produce short gamma-ray bursts. The decades-old theory was right. But the detection did something else. It gave astronomers a target, a specific galaxy, somewhere in that 30 square degree patch where the merger had just happened. And if the models were correct, that galaxy should now be hosting a glowing cloud of radioactive debris, a kilonova, that would be visible to optical and infrared telescopes for days or weeks. The race was on to find it. The first optical detection came roughly 11 hours after the gravitational wave signal, once the target region of sky had rotated into darkness for ground-based telescopes in the southern hemisphere. A team using the 1-meter SWOPE telescope at Las Campanas Observatory in Chile identified a new point of light in the galaxy NGC 4993, a lenticular galaxy in the constellation Hydra. The object had not been there in previous images of the galaxy. It was bright, blue, and sitting in the galaxy's outer regions, exactly the kind of location where you would expect to find a transient event rather than a stable star. Within hours, other teams confirmed the detection. The transient was catalogued as 82017 GFO, and within a day dozens of telescopes on every continent and in space were pointed at it. NGC 4993 is not a famous galaxy. It is not particularly large or bright or unusual. It sits roughly 130 million light-years from Earth, close enough that its stars are individually resolvable with large telescopes, far enough that it had never been the subject of intense study. Before August 17, 2017, most astronomers could not have told you anything about it. After that day, it became one of the most observed galaxies in the history of astronomy. Over the next several weeks, more than 70 observatories participated in follow-up observations, covering every part of the electromagnetic spectrum, from radio waves to gamma rays. It was the most comprehensive multi-wavelength observation of a single transient event ever conducted. Hubble Space Telescope imaged the Kilonova in optical and near-infrared wavelengths, tracking how its brightness and color evolved over time. Spitzer Space Telescope watched in the mid-infrared. Chandra X Ray Observatory searched for X-ray emission from the collision site. Radio telescopes, including the Very Large Array in New Mexico and the Australia Telescope Compact Array, monitored the source at centimeter and millimeter wavelengths. Ground-based optical telescopes, too many to list, individually contributed photometry and spectroscopy, measuring the brightness and the spectrum of the light coming from the debris. Every observation added another piece to the puzzle, and what emerged was a picture that matched the theoretical predictions almost perfectly. The Kilonova was real. The models had been right. The significance of this cannot be overstated. For the first time in history, astronomers had observed a single cosmic event using every available type of messenger. Gravitational waves, which travel freely through the universe unaffected by matter or magnetic fields. Photons, particles of light spanning the entire electromagnetic spectrum. And neutrinos, though in this case no neutrino detectors registered a signal, likely because the event was too far away and the neutrino flux too weak. But the principle was established. Multi-messenger astronomy was no longer a theoretical idea, it was a reality. Different branches of physics, using completely different instruments, had converged on the same event and told a single coherent story. The gravitational wave signal told astronomers the masses of the two neutron stars, roughly 1.4 and 1.3 solar masses, close enough to be nearly equal. It told them the distance to the event, about 40 megaparsecs or 130 million light-years, calculated from the amplitude of the signal. It told them how fast the stars were orbiting each other in the final moments before merger, hundreds of times per second. And it told them the moment of coalescence, the instant when the two objects finally touched. All of that information was encoded in the shape of the waveform, the chirp, and extracted using sophisticated data analysis techniques that compared the observed signal to a vast library of theoretical templates. The gamma-ray burst told a different part of the story. The burst was weak compared to typical short gamma-ray bursts, only about 1/1000th as bright as the average. That weakness was itself informative. It suggested that Earth was not looking straight down the barrel of the relativistic jet, but was instead viewing the event from an angle, off-axis. If the jet had been pointed directly at us, the gamma rays would have been far more intense. The fact that we saw a weak burst meant the jet existed, confirming the theoretical models, but that we were catching only the edge of the beam. This off-axis geometry became a critical piece of interpreting the rest of the data. The optical and infrared observations showed a rapidly evolving transient. The light started out blue, peaked in brightness within a day, then faded and reddened over the following weeks. The color evolution was a smoking gun for the Kilonova interpretation. The debris ejected during the merger is rich in neutrons, and those neutrons quickly combine with protons to form heavy, unstable nuclei. The nuclei decay, releasing energy, and that energy heats the debris cloud from within. The cloud glows, not from ongoing fusion or shock heating, but from radioactive decay. It is essentially a nuclear bomb in slow motion, spreading outward at thousands of kilometers per second and cooling as it expands. The initial blue color indicated that the outer layers of the debris were relatively light, composed of elements like strontium and zirconium. These lighter elements have relatively simple atomic structures, and their opacity is low, meaning light can escape easily. As the cloud expanded and cooled, heavier elements deeper in the ejecta became visible. These heavier elements, things like gold, platinum, uranium, have far more complex electron structures, and they absorb and scatter light much more efficiently. The increased opacity caused the light to shift toward the red and infrared. By the second week, the Kilonova was radiating most of its energy in the infrared, invisible to the human eye but bright to telescopes equipped with infrared cameras. Spectroscopy, the technique of splitting light into its component wavelengths, revealed broad features that were difficult to interpret in detail but consistent with a mix of heavy elements. The problem with heavy element spectra is that they are incredibly complicated. A single atom of gold or platinum has dozens of electrons, and those electrons can transition between energy levels in an enormous number of ways. The result is a spectrum with thousands or even millions of overlapping lines that blend together into a nearly featureless continuum. But even that featureless continuum carries information. The overall shape, the color, the rate of fading, all of it matched the predictions for debris rich in so-called Ra process elements, elements formed by the rapid neutron capture process. The R process is the only known way to build the heaviest elements in the universe. Elements heavier than iron cannot be made by normal fusion inside stars. Fusion stops at iron because fusing iron costs energy rather than releasing it. Stars can make elements up to iron by progressively fusing lighter nuclei in their cores, but anything heavier requires a different mechanism. There are two main processes. The C process, or slow neutron capture, happens inside aging giant stars where neutrons are added to atomic nuclei one at a time over thousands of years. The S process can build elements up to lead and bismuth, but it cannot go much further. The R process, rapid neutron capture, happens in environments so flooded with neutrons that nuclei can capture dozens of them in a fraction of a second before they have time to decay. The R process builds the heaviest stable and unstable elements, including uranium and thorium. For decades, astronomers argued about where the R process happens. Supernovae were the obvious candidate, but the conditions inside a supernova are extraordinarily complicated, and it was never clear that they produced enough neutrons in the right place at the right time. Neutron star mergers offered a cleaner picture. When two neutron stars collide, they eject material that is almost pure neutrons. A neutron-rich environment is exactly what the process needs. The models predicted that a single neutron star merger should produce somewhere between 1/100th and 1/10th of a solar mass worth of heavy elements, with a significant fraction of that being gold and platinum. The total mass of gold produced in a single merger like GW170817 is estimated at several Earth masses. Tens of billions of tons, more gold than humanity has ever mined in all of recorded history, forged in a few seconds of violence and scattered across space. The detection of GW170817 provided the first direct observational evidence that this picture is correct. The Kilonova light curve, the way the brightness changed over time, matched the predictions for R process-powered emission. The spectral features, vague as they were consistent with heavy elements, and the total amount of ejected material inferred from the observations was in the right range. Neutron star mergers do produce heavy elements. They do scatter that material into space, And over billions of years, as more and more mergers happen across the universe, that material gets incorporated into new generations of stars and planets. The gold in your jewelry, the platinum in your car's catalytic converter, the uranium in nuclear reactors, all of it came from events like this one, from the collision of two dead stars in some distant galaxy billions of years ago. But the observations also revealed something unexpected. The gamma-ray burst was weaker than it should have been, and the X-ray and radio emission from the event took weeks to brighten. This was not what the standard models predicted. If the merger had produced a narrow relativistic jet, and the jet was pointed even slightly away from Earth, you would still expect to see X-rays and radio waves from the interaction between the jet and the surrounding gas. That emission should have peaked within a few days. Instead, it took about 2 weeks for the X-rays to become detectable and more than a month for the radio emission to reach its peak. The delayed brightening suggested that something more complicated was happening. The jet might have been choked, smothered by the debris cloud surrounding the merger, or it might have been structured, with different speeds and energies at different angles. The details are still being argued over, but the basic message was clear. Neutron star mergers are messier than the simplified models suggested. The event also became a cosmological tool. Because gravitational waves carry information about distance, the amplitude of the wave tells you how far away the source is, and because the Kilonova was visible, astronomers could identify the host galaxy and measure its redshift, how fast it is receding from us due to the expansion of the universe. Combine distance and redshift and you get a measurement of the Hubble constant, the rate at which the universe is expanding. This technique, using gravitational waves as standard sirens, had been proposed decades earlier but never demonstrated. GW170817 was the first real application. The result gave a Hubble constant of roughly 70 kilometers per second per megaparsec, sitting right in the middle of the ongoing tension between measurements from the cosmic microwave background and measurements from the cosmic distance ladder. One event is not enough to settle that debate, but it proved the method works. Future detections will improve the precision. Then there was the test of fundamental physics. Gravitational waves and light both travel at finite speeds, and according to general relativity, they should travel at exactly the same speed, the speed of light. But some alternative theories of gravity predict small differences. If gravitational waves traveled even slightly faster or slower than photons, the difference would accumulate over a journey of 130 million light-years. The gravitational wave signal and the gamma-ray burst arrived within 2 seconds of each other after traveling for 130 million years. That timing constrained the difference in speed to less than 1 part in 10 to the 15th. They travel at the same speed to within an absurdly small margin. The result ruled out or severely constrained a number of modified gravity theories that had been proposed as alternatives to general relativity. Einstein once again was right. Robert Quimby, an astronomer who was not part of the discovery team but commented on the findings, noted that GW170817 represented the first truly independent verification of a gravitational wave source. The earlier black hole detections had been groundbreaking, but they relied entirely on gravitational wave data. You could not check them with a telescope. They were invisible. Neutron stars, by merging in a way that produces light, gave astronomers a way to verify the gravitational wave detection using completely independent methods. If the gravitational wave signal was real, there should be light. There was light. The two observations matched. That cross-check removed any lingering doubt about whether LIGO and Virgo were really detecting gravitational waves or just seeing noise. The event was a turning point. Within hours of the public announcement, which came on October 16, 2017, nearly 2 months after the detection, Headlines around the world described it as the dawn of a new era in astronomy, multi-messenger astronomy. The ability to observe the universe using all available messengers, gravitational waves, electromagnetic radiation, and potentially neutrinos. For more than 4 centuries, astronomy had been almost entirely an electromagnetic science. Telescopes collected light, radio dishes collected radio waves, X-ray satellites collected X-rays, all photons, all variations on the same theme. Gravitational waves were different. They were not electromagnetic. They did not interact with matter the way light does. They passed through dust, gas, magnetic fields, black hole event horizons, everything. They carried information from regions of the universe that are completely dark to traditional telescopes. Combining gravitational wave observations with electromagnetic observations gave astronomers a far richer picture than either method could provide alone. The collaboration required to pull off the follow-up observations was extraordinary. Within minutes of the LIGO-Virgo alert going out, observatories on every continent began coordinating their response. Who had the right instruments? Who had access to the part of the sky where the source was located? Who could observe first? The target region was in the southern hemisphere sky, which meant telescopes in Chile, South Africa, and Australia had the first shot. But as the Earth rotated, other sites came online. Observations continued around the clock for weeks. Teams shared data in real time, posting results to online platforms so that everyone could see what everyone else was finding. It was an unprecedented level of coordination, and it worked. The result was a dataset so rich and comprehensive that papers analyzing GW170817 are still being published years later. The discovery earned the Nobel Prize in Physics in 2017, though that prize went to the founders of LIGO for the earlier detection of gravitational waves from black hole mergers. GW170817 came after the Nobel announcement, but it validated everything the prize had recognized. Gravitational wave astronomy was not just possible, it was transformative. And neutron star mergers, the events that produce both gravitational waves and light, turned out to be even more important than anyone had predicted. They were not just collisions. They were laboratories, cosmic experiments running at conditions no human technology could ever replicate, forging the heaviest elements and scattering them into space. The gamma-ray burst, weak as it was, confirmed that short gamma-ray bursts come from neutron star mergers. The Kilonova, glowing in optical and infrared light, confirmed that neutron star mergers produce heavy elements. The gravitational wave signal confirmed that the inspiral and merger happened exactly the way general relativity predicted, and the combined observations gave astronomers a new way to measure the expansion of the universe. One event, 4 major confirmations, and a completely new way of studying the cosmos. That is why August 17, 2017 is a date that will appear in textbooks for as long as there are textbooks. And yet, for all the answers GW170817 provided, it also raised new questions. The gamma-ray burst was weaker than expected. The X-rays and radio waves arrived late. The jet, if there was one, did not behave the way the simplest models said it should. The kilonova was brighter and bluer in the first few hours than some models predicted, and the total mass of the merged object, roughly 2.7 solar masses, sat right on the edge of the threshold where theory says a neutron star should collapse into a black hole. Did it collapse immediately? Did it survive for a few seconds as a hypermassive neutron star before collapsing? The gravitational wave signal cut off at the moment of merger, so there was no direct evidence either way. But the details mattered, because the details tell you about the physics of matter at densities higher than anything else in the universe. Neutron star material, nuclear matter, pushed to its absolute limits. The afterglow, the cooling debris cloud, was still visible for weeks. The glow faded, shifted deeper into the infrared, and eventually dropped below the detection threshold of even the most sensitive telescopes. But the material is still there, spreading outward into space, cooling, darkening, carrying several Earth masses of gold and platinum and uranium with it. Billions of years from now, some of that material will be incorporated into a new star system. Maybe a planet will form from it. Maybe on that planet, someone will dig up a piece of gold and wonder where it came from. They will not know. But we do. It came from a collision. Two neutron stars, remnants of supernovae that exploded millions of years before the dinosaurs, finally fell into each other after orbiting for hundreds of millions of years, and for a brief moment, they lit up the universe. The light showed up first. That is the detail everyone remembers when they talk about the Kilonova from GW 170817, the fact that after 130 million years of travel, after crossing distances so vast that the light had been on its way since before the continents had finished arranging themselves into their current shapes, it arrived quietly, right on schedule, in the field of view of a telescope in Chile roughly 11 hours after the gravitational wave detectors had heard the merger, a new point of light where no light had been before. Blue at first, bright, sitting in the outer regions of an otherwise unremarkable galaxy in the constellation Hydra. Within hours, dozens of other telescopes had confirmed it. Within days, every major observatory on the planet and in orbit had turned to look. And what they saw was not a supernova. It was something rarer, stranger, and in some ways more important. A kilonova, the birth cry of the heaviest elements in the universe, forged in conditions so extreme that nowhere else in nature, not inside stars, not in supernova explosions, not anywhere, can reproduce them. The word kilonova is deliberate. A nova, the classical kind, happens when a white dwarf in a binary system siphons gas off its companion star. The gas piles up on the white dwarf's surface, gets compressed and heated, and eventually ignites in a runaway thermonuclear explosion. The explosion blows the outer layer off the white dwarf, but leaves the core intact. The star survives. The brightness spikes, peaks at roughly 10,000 to 100,000 times the luminosity of the sun, and then fades over weeks or months. Novae are common. The Milky Way probably hosts a few dozen of them per year, though most go unnoticed because they happen too far away or behind too much dust. They are bright, but they are not catastrophic. The white dwarf loses a little mass, cools down, and goes back to pulling gas off its companion. The cycle repeats. Some novae are recurrent, same star, same explosion, decades apart. A supernova is a different beast entirely. A supernova is the death of a star. Either the core of a massive star collapses and the outer layers rebound in a core collapse supernova, or a white dwarf accretes enough mass to tip over the Chandrasekhar limit and collapses, igniting a runaway fusion reaction that obliterates the entire star in a type Ia supernova. Supernovae are violent. At peak brightness, a supernova can reach 5 to 10 billion times the luminosity of the Sun, bright enough to outshine every other star in its host galaxy combined. They fade slowly, over months, powered first by the shockwave tearing through the star's outer layers, and later by the radioactive decay of nickel-56 and cobalt-56 synthesized in the explosion. Supernovae are the universe's heavy element factories, the forges where carbon, oxygen, silicon, iron, and dozens of other elements are made and scattered into space. Everything heavier than helium in your body came from a supernova at some point in the past. They are rare. A galaxy the size of the Milky Way might host 1 or 2 per century. A kilonova sits in between. The name means 1,000 novae. a reference to the fact that a kilonova is roughly 1,000 times brighter than a classical nova, but still significantly dimmer than a supernova. Peak luminosity is typically a few hundred million to a few billion times the sun's output, depending on the specifics of the merger. Bright enough to be seen across hundreds of millions of light-years with modern telescopes, but not bright enough to be mistaken for a supernova. The light curve is faster. A kilonova brightens over the first day, peaks, and then fades over the course of a week or two. A supernova takes weeks to reach maximum brightness and months to fade. A kilonova is a quick flash by comparison, a brief flare of light and then darkness, but that brief flare carries information that supernovae cannot provide because the light from a kilonova is powered by something fundamentally different. Supernovae are powered by shock heating and radioactive decay of relatively light elements like nickel and cobalt. Kilonovae are powered by the radioactive decay of the heaviest elements in the periodic table: gold, platinum, uranium, thorium. Elements so heavy and so unstable that they cannot exist for long without decaying into lighter nuclei. The decay releases energy, alpha particles, beta particles, gamma rays. That energy heats the expanding debris cloud from within, and the cloud radiates. It glows not because it is being heated by an external source or by ongoing fusion, but because the nuclei themselves are falling apart and releasing the energy stored in their structure. It is a nuclear glow. The entire cloud is a slow-motion dirty bomb, spreading outward at thousands of kilometers per second, cooling as it expands, fading as the radioactive isotopes decay into stable forms. The color of a kilonova is distinctive. Early on, in the first few hours, the outer layers of the debris are relatively light. Elements like strontium, yttrium, zirconium. These are still heavy by stellar standards, heavier than anything that comes out of a normal supernova, but they are not gold or platinum. They have simpler atomic structures, fewer electrons, and they are less opaque. Light can escape more easily. The result is a blue or cyan glow, similar in color to a very hot star, but as the debris expands and cools, the heavier material deeper in the ejecta becomes visible. Gold has 79 protons and 79 electrons. Platinum has 78. Uranium has 92. These atoms have extraordinarily complex electron structures, and those electrons interact with light in complicated ways. They absorb photons across a huge range of wavelengths, scattering and re-emitting the light in all directions. The opacity of heavy elements is enormous. A cloud of gas rich in gold and platinum is nearly opaque to visible light. The effect is that as the kilonova evolves, the light shifts toward the red and infrared. By the second day, the visible light has faded significantly, and most of the emission is coming out in the near-infrared. By the end of the first week, the kilonova is glowing primarily in the mid-infrared, invisible to the human eye but bright to telescopes equipped with infrared cameras. The color shift is a smoking gun. If you see a transient that starts blue and quickly reddens over the course of a few days, and if the brightness and duration match the predictions for a radioactively powered event, you are almost certainly looking at a kilonova. The spectral signature, the detailed pattern of absorption and emission lines, is harder to interpret because heavy elements produce so many overlapping lines that the spectrum becomes a nearly featureless continuum. But even that featureless continuum is informative. It tells you that the debris contains a mix of very heavy elements, exactly what you would expect if the debris came from a neutron star merger. The AT2017 GFO kilonova, the one associated with GW170817, followed this script almost perfectly. The first optical observations showed a bright blue transient that peaked within about a day. The color temperature, the effective temperature inferred from the spectrum, was around 8,000 to 10,000 Kelvin, roughly the surface temperature of a hot blue star. Over the next few days, the light faded and reddened. By day 3, the peak emission had shifted into the near-infrared. By day 7, most of the luminosity was coming out at wavelengths longer than about 1 micron, well into the infrared. Hubble Space Telescope and Spitzer Space Telescope tracked the fading glow for weeks, watching it cool and dim until it finally dropped below the detection threshold. The total energy radiated over the course of the event was enormous, roughly 10 to the 42 ergs, comparable to the energy output of a bright supernova but released over a much shorter timescale. The light was powered by radioactive decay. Specifically, it was powered by the decay of unstable heavy nuclei synthesized during the merger. When two neutron stars collide, they do not just smash together and disappear into a black hole. The collision is messy. The outer layers of both stars, material that is not quite dense enough to be locked into the core, gets flung outward at high speed. Some of it is ejected during the final moments of the in-spiral as tidal forces stretch and deform the stars. More is ejected during the actual collision as the two objects slam together and rebound. The debris forms a rapidly expanding cloud, a shell of neutron-rich matter spreading outward at speeds ranging from 10 to 30% the speed of light, tens of thousands of kilometers per second. That debris is the raw material for a kilonova. The key to understanding what happens next is the neutron-to-proton ratio. Normal matter, the kind that makes up stars and planets and people, has roughly equal numbers of protons and neutrons. Hydrogen has 1 proton and 0 neutrons. Carbon has 6 protons and 6 neutrons. Iron has 26 protons and 30 neutrons. The ratio varies a bit, but it stays in a reasonable range. Neutron star material is different. Neutron stars are made almost entirely of neutrons. The electrons and protons that were present in the original stellar core got crushed together during the core collapse supernova, forming neutrons and releasing neutrinos. What is left is a sea of neutrons with only a thin crust of normal matter on the surface. When you eject material from a neutron star, you are ejecting neutron-rich matter. The neutron-to-proton ratio is extreme, far higher than anything you would find in a normal star. That extreme neutron richness is exactly what you need to build heavy elements. The process is called rapid neutron capture, or the R process for short. The R stands for rapid, meaning the neutron captures happen faster than the timescale for radioactive decay. Here is how it works. Start with a seed nucleus, something relatively light like iron or nickel. Flood it with neutrons. The nucleus captures a neutron and becomes heavier. Normally, a neutron-rich nucleus is unstable and will decay via beta decay, where a neutron turns into a proton, an electron, and an antineutrino. But if the neutron density is high enough, the nucleus can capture another neutron before it has time to decay. Then another, then another. The nucleus gets heavier and heavier, piling on neutrons faster than it can shed them. Eventually, you reach a point where the nucleus is so neutron-rich that it cannot hold together anymore, and it undergoes fission or splits into smaller pieces. But before that happens, you have built a very heavy, very neutron-rich nucleus. Once the neutron flood stops, the nucleus starts decaying. Beta decay. One neutron at a time turns into a proton. The nucleus climbs up the periodic table, shifting from one element to the next until it reaches a stable configuration. The end result is a stable heavy element, gold, platinum, uranium, whatever the decay chain leads to. The R process requires 3 things. First, a very high neutron density. You need enough free neutrons that the seed nuclei are constantly being bombarded. Second, a high temperature. The nuclei need to be moving fast enough that when they collide with neutrons, the neutrons actually stick rather than just bouncing off. Third, rapid expansion. The neutron-rich environment cannot last forever. If the material sits around too long, the neutrons will decay into protons, the neutron density will drop, and the R process will stop before you have built anything interesting. You need the process to run fast, build the heavy nuclei, and then stop, freeze out. Let the unstable nuclei decay into their stable forms while the material expands and cools. Neutron star mergers provide all three conditions. The collision ejects material that is almost pure neutrons. Neutron density check. The material is heated to billions of degrees by the violence of the collision. Temperature check. The debris is expanding at a significant fraction of the speed of light, so the neutron-rich phase lasts only a few seconds before the material thins out and cools below the threshold where neutron capture can continue. Rapid expansion check. The process runs for a few seconds, builds nuclei all the way up to uranium and beyond, and then shuts off. The debris continues expanding, now carrying a payload of freshly synthesized heavy elements. Those elements are unstable. They decay. The decay heats the debris. The debris glows. That glow is the kilonova. The amount of heavy elements produced in a single neutron star merger is staggering. The estimates vary depending on the model and the assumptions about the mass and composition of the ejector, but the numbers are consistent enough to paint a clear picture. A typical neutron star merger ejects somewhere between 1/100th and 1/10th of a solar mass of material. That is a lot. 1/100th of a solar mass is about 300 times the mass of Earth. 1/10th of a solar mass is 3,000 Earth masses. Most of that ejected mass is in the form of heavy elements, the products of R process nucleosynthesis, and a significant fraction of those heavy elements are in the gold and platinum range. The exact percentages depend on the details, but the best estimates say that a single merger produces somewhere between 10 and a few hundred Earth masses of gold. Let me say that again because it is worth pausing on. One neutron star merger can produce tens to hundreds of Earth masses of gold. That is not a typo, that is not an exaggeration. One event, lasting a few seconds, forges more gold than you would get if you took the entire planet Earth and turned every atom of it into gold. Multiple Earths worth. And that gold is scattered into space at thousands of kilometers per second, spreading out into a shell that will eventually mix with the surrounding interstellar gas and be incorporated into the next generation of stars and planets. Do this enough times over the history of the universe, and you can explain where all the gold in the cosmos came from. Every gold ring, every gold coin, every gold filling in every tooth, all of it came from neutron star mergers. There is no other source that works. Supernovae do not produce enough. The R process in supernovae, if it happens at all, is marginal. Neutron star mergers are the smoking gun. The same story applies to platinum, which is even heavier than gold, and to uranium and thorium, the heaviest naturally occurring elements. The abundance patterns in the solar system, the relative amounts of different heavy elements we see when we analyze meteorites or the sun spectrum, match the predictions for R process nucleosynthesis almost perfectly. For decades, that match was a hint that the Beer process was happening somewhere, but nobody knew where. Neutron star mergers were a candidate, but they were rare and nobody had ever seen one produce heavy elements. The 2017 Kilonova changed that. The spectral features, vague as they were consistent with a mix of heavy R process elements. The color evolution, blue to red to infrared, matched the predictions for debris rich in gold and platinum. The total luminosity and the rate of fading matched the expected energy release from radioactive decay of unstable heavy nuclei. Everything fit. Neutron star mergers make the heavy elements. Case closed. Edu Berger, an astronomer at Harvard who was part of the team studying the Kilonova, called it the first direct fingerprints of the creation of heavy elements, not indirect, not inferred, direct. The light coming from the Kilonova was literally the glow of freshly made gold and platinum cooling and decaying in real time. Ryan Foley, an astronomer at the University of California, Santa Cruz, put it more plainly: "The gold in your wedding ring came from merging neutron stars." That quote made headlines because it is concrete, it is personal. You can hold a piece of gold in your hand and know with certainty that it was made in an event like this one, not metaphorically, literally. The atoms were forged in a collision between two dead stars, ejected into space, drifted through the galaxy for hundreds of millions or billions of years, and eventually found their way into the cloud of gas that collapsed to form the Sun and the planets, including Earth, including you. The implications for galactic chemical evolution are enormous. Chemical evolution is the process by which galaxies accumulate heavier elements over time. The universe started with hydrogen and helium and traces of lithium. That was it. Everything heavier had to be made inside stars or in stellar explosions. The first generation of stars, the ones that formed from primordial gas, contained no heavy elements at all. They fused hydrogen into helium, helium into carbon, carbon into oxygen, all the way up to iron in the most massive cases. When they exploded, they scattered those newly made elements into space. The next generation of stars formed from gas that was slightly enriched in heavy elements. Those stars made more heavy elements, exploded, and enriched the gas further. Over billions of years, the interstellar medium became progressively richer in carbon, oxygen, silicon, iron, and all the other products of stellar nucleosynthesis. But the heaviest elements, the ones heavier than iron, were a puzzle. Supernovae make some of them through the C process, slow neutron capture, which happens in the outer layers of certain dying stars. But the SAS process cannot build the very heavy elements like gold and uranium. Those require the R process, and the R process requires conditions that supernovae might not provide. Neutron star mergers do, and now we know they happen often enough to explain the observed abundances. A galaxy like the Milky Way probably hosts a neutron star merger roughly once every 10,000 to 100,000 years. That sounds rare, and it is compared to supernovae, which happen once every few decades. But over the 10-billion-year history of the galaxy, 100,000 mergers is a lot. Each one dumps tens to hundreds of Earth masses of heavy elements into the interstellar medium. Add it all up, and you get the observed abundances of gold, platinum, and uranium in the galaxy today. Vinicius Placo, an astronomer who studies the chemical evolution of stars, noted that the Kilonova observations strongly indicate that many of the heavy chemical elements found in nature were produced by Kilonova explosions. Not some, many, possibly most. The R process elements we see in the Sun, in the Earth, in meteorites, in ancient stars that formed billions of years ago, all of them likely came from neutron star mergers. That statement would have been speculative before 2017. After the Kilonova detection, it became the standard model. Textbooks are being rewritten to include Kilonova as a major, perhaps the major, source of R process elements. There is also a subtler point that astronomers are still working out. The distribution of heavy elements in a galaxy is not uniform. Some regions are richer in heavy elements than others. The variation depends on the history of star formation and stellar explosions in each region. Neutron star mergers, because they eject so much material at such high speed, can pollute a large volume of space around the merger site. The debris expands outward, mixes with the surrounding gas, and affects the composition of the next generation of stars that form nearby. Stars that form from gas polluted by a recent neutron star merger will have higher abundances of R process elements than stars that formed elsewhere. Astronomers have found a few ancient stars in the Milky Way with unusual abundance patterns, very high levels of R process elements compared to iron or other lighter elements. Those stars might have formed from gas that was directly enriched by a neutron star merger shortly before the stars themselves were born. They are fossils, carrying the chemical fingerprints of a collision that happened billions of years ago. The spectral signature of a kilonova is tricky. Heavy elements produce absurdly complicated spectra. An atom of gold has 79 electrons, and those electrons can transition between a huge number of energy levels. Each transition corresponds to a spectral line, and gold alone produces hundreds of thousands of lines spread across a wide range of wavelengths. Platinum, uranium, all the other heavy R process elements, they all do the same thing. When you have a mix of dozens of different heavy elements all radiating at once, the individual lines overlap and blend together into a nearly featureless continuum. You lose the sharp features that make spectroscopy useful. What you are left with is a broad, smooth spectrum that tells you the temperature and the general composition, but not the detailed abundances of individual elements. That is exactly what observers saw in AT 2017 GFO. The early spectrum was relatively smooth, with some broad features that might have been absorption or emission from lighter R process elements like strontium or cesium. As the kilonova evolved and the light shifted into the infrared, the spectrum became even smoother, featureless. The best match to the data came from models that assumed a mix of heavy R process elements with a composition similar to what you get if you run an R process nucleosynthesis calculation starting from neutron-rich seed nuclei. The models could not tell you exactly how much gold versus platinum versus uranium was present. The spectra were too blended, but they could tell you that the heavy elements were there in roughly the proportions the R process predicts. That was enough. It matched. The kilonova was producing exactly the kind of light you would expect from debris loaded with freshly synthesized heavy elements. The luminosity of a kilonova is tied directly to the mass of radioactive material in the ejector. More heavy elements means more decay energy, means a brighter kilonova. Less heavy elements, dimmer kilonova. The relationship is not perfectly linear because the opacity of the debris also matters. If the debris is very opaque, the light has a harder time escaping, and the kilonova appears dimmer than it otherwise would. But to first order, the brightness tells you how much radioactive material is present. For AT 2017 GFO, the peak luminosity was about a few times 10 to the 41 erg per second, which corresponds to several 100 million times the sun's luminosity. Bright, but not supernova bright. The total energy radiated over the entire event was roughly 10 to the 42 erg, about 1/10,000th the energy of a typical supernova. That energy came from the decay of unstable heavy nuclei, and the amount of energy released is directly related to the mass of those nuclei. The best fits to the data suggested that the kilonova ejected somewhere around a few hundredths of a solar mass of heavy elements, with a significant fraction of that being in the gold and platinum mass range. 10 to 16,000 Earth masses of heavy elements total, depending on which analysis you trust. At least 10 Earth masses of gold, possibly more. Some estimates push the gold yield higher, into the tens or even hundreds of Earth masses, but those are model-dependent and rely on assumptions about the composition and geometry of the ejector that are hard to verify. The safe statement is that a single neutron star merger produces at minimum several Earth masses of gold. That is conservative. The upper end could be much higher. The duration of a kilonova is short. A week or two of detectable emission, then darkness. The fading happens because the debris is expanding. As it expands, it cools. As it cools, the rate of photon emission drops. The radioactive decay continues, but the energy is being spread over a larger and larger volume, and eventually the debris becomes too diffuse and too cool to radiate efficiently. The heavy elements are still there, they are still decaying. But the light output drops below the detection threshold of even the most sensitive telescopes. The kilonova goes dark not because the process has stopped, but because we can no longer see it. The debris continues spreading outward for thousands or millions of years, mixing with the surrounding interstellar gas, until eventually it becomes indistinguishable from the background. By that point, the unstable isotopes have decayed into stable forms. The gold is just gold. The platinum is just platinum, ready to be incorporated into a new star, a new planet, a new solar system. And that is where the story connects back to Earth. The solar system formed about 4.5 billion years ago from a collapsing cloud of gas and dust. That gas was enriched with heavy elements from previous generations of stars and stellar explosions. Some of those heavy elements came from supernovae. Some came from neutron star mergers. We do not know the exact mix, but the abundance patterns suggest that at least a few neutron star mergers contributed to the material that eventually became the Sun and the planets. The gold in the Earth's crust, the platinum in catalytic converters, the uranium in nuclear reactors, all of it came from mergers that happened billions of years ago in the galaxy's distant past. Events just like GW170817 playing out over and over across cosmic time, seeding the universe with the raw materials for planets and eventually for life. The kilonova is more than just a fireball. It is a cosmic transmutation. Dead stars colliding, matter compressed to impossible densities, nuclei flooded with neutrons and built up into the heaviest elements the universe allows, then scattered across light years of space to drift and cool and wait until gravity pulls them back together into something new. Every heavy element on Earth followed that path, forged in violence, ejected in chaos, incorporated into a planet where, billions of years later, something calling itself human dug it up, melted it down, and turned it into jewelry and electronics and art. The kilonova is the origin story, the collision is the forge, and the light, that brief blue-red infrared glow that fades over days and disappears into the dark, is the signal. The announcement that somewhere in the universe the heaviest elements have just been made. But the kilonova is not the only thing a neutron star merger produces. The light we see, the glow of radioactive decay, is the aftermath. During the collision itself, in the moments when the two stars are actually touching, something else happens, something faster, hotter, and far more violent. The merger does not just eject debris at thousands of kilometers per second, it launches jets, beams of matter and energy moving at nearly the speed of light, ripping through space with enough power to briefly outshine the entire galaxy. Those jets are the subject of what comes next. The kilonova is the aftermath. The glow, the radioactive decay, the slow fade into infrared darkness, all of it is what happens after the violence. It is the cooling, the cleanup, the universe sweeping debris under the rug and waiting for someone with a telescope to notice. But during the collision itself, in those first few seconds when two neutron stars are actually merging, tearing each other apart, compressing matter to densities that make normal physics sit down and shut up, something else is happening, something faster, something that does not glow gently in the optical and infrared, something that screams. The jets arrive before anyone has time to process what the gravitational wave detectors just heard. Less than 2 seconds after the chirp cuts off, gamma-ray telescopes in orbit pick up a flash, a short gamma-ray burst. Brief, intense, gone before you can blink. The burst that accompanied GW170817 lasted about 2 seconds and carried enough energy to power our sun for weeks. That flash was not coming from the Kilonova. The Kilonova had not even started glowing yet. The gamma rays came from something else. A beam of matter and energy launched from the collision site, moving at 99.9% the speed of light or faster, ripping through space with a ferocity that makes supernovae look polite by comparison. That beam is a relativistic jet, and it is one of the most extreme phenomena in the known universe. Relativistic jets are not unique to neutron star mergers. They show up all over the place in astrophysics, wherever you have a compact object accreting matter at a furious rate. Active galactic nuclei, the supermassive black holes at the centers of galaxies, produce jets that stretch for millions of light years. Smaller stellar mass black holes in binary systems produce jets on smaller scales but with similar physics. Even young stars, protostars still forming from collapsing gas clouds, can launch jets. But the jets from neutron star mergers are special because of the environment they are born into. You are not dealing with a stable accretion disk around a slowly feeding black hole. You are dealing with the chaotic wreckage of 2 neutron stars that just collided at a significant fraction of the speed of light. The magnetic fields are tangled and ferocious, the matter is neutron-rich and superheated, and the energy available, the gravitational potential energy of the system, is staggering. Everything about the setup is extreme, and the jets reflect that. The jet forms in the immediate aftermath of the merger. The 2 neutron stars have touched, their outer layers have been flung outward as the Kilonova ejector, and what is left is a hot, dense, spinning core. Depending on the total mass of the system, that core might survive for a few seconds as a hypermassive neutron star, held up temporarily by rapid rotation and thermal pressure, or it might collapse immediately into a black hole. Either way, not all of the material makes it into the remnant. Some of it, perhaps a few hundredths of a solar mass, ends up in orbit. It forms an accretion disk, a swirling ring of neutron-rich gas spiraling inward toward the central object. The disk is hot. Temperatures reach billions of degrees. The matter is moving fast, a significant fraction of the speed of light in the inner regions, and the disk is threaded with magnetic fields. Magnetic fields are the key. Without magnetic fields, accretion disks just radiate their energy away and the infalling matter spirals inward relatively quietly. With magnetic fields, especially strong ones, the physics gets interesting. The fields get twisted by the rotation of the disk. They get amplified by dynamo processes, feedback loops where the motion of the conducting gas strengthens the field and the field affects the motion of the gas. The result is a tangled, churning magnetic structure that channels energy and matter in specific directions. In the case of a neutron star merger, the fields channel material along the rotation axis perpendicular to the plane of the disk. Matter gets squeezed into narrow funnels along the magnetic poles, accelerated to absurd speeds and shot outward. That is the jet. The acceleration mechanism is still debated, but the leading models involve a combination of magnetic pressure and radiation pressure. The magnetic fields themselves can exert force on the charged particles in the jet, electrons, positrons, protons. Think of it like a railgun. The magnetic field acts as a guide and an accelerator, pushing particles along the field lines and accelerating them to relativistic speeds. At the same time, the intense radiation field near the remnant, photons pouring off the hot accretion disk, can scatter off particles and transfer momentum. The combination is enough to push jet material to speeds that approach the ultimate cosmic speed limit, 99% the speed of light. 99.9%. Some observations suggest velocities even closer than that. One gamma-ray burst in 2007, not from a neutron star merger but from a different kind of event, showed jet material moving at 99.997% the speed of light. 6 nines, that is fast enough that time dilation becomes so extreme that a clock on the jet would tick thousands of times slower than a clock at rest. Fast enough that distances in the direction of travel are compressed by factors of hundreds or thousands. The universe, from the perspective of a particle in that jet, is a thin pancake. Relativistic motion does strange things to light. When something is moving toward you at close to the speed of light, the light it emits gets compressed, blue-shifted, and concentrated into a narrow cone pointing in the direction of motion. This effect is called relativistic beaming. The faster the object moves, the narrower the cone. If a jet is moving at 99.9% the speed of light, the emission is beamed into a cone with an opening angle of only a few degrees. That means if the jet is pointed at you, it looks incredibly bright. All the energy that would normally be spread out over the entire sky is concentrated into a tiny patch. If the jet is not pointed at you, you see almost nothing. The jet could be just as energetic, just as powerful, but if it is aimed 10 degrees to the side, you miss it entirely. This is why gamma-ray bursts are so unpredictable. They are not rare, they are just narrow. Most of them are pointed somewhere else. GW170817 gave astronomers their first clear look at what happens when you catch a neutron-star merger from an off-axis angle. The gamma-ray burst was detected, but it was weak, much weaker than typical short gamma-ray bursts. The usual short burst has a peak luminosity of about 10 to the 51 erg per second. The burst from GW170817 peaked at about 10 to the 47 erg per second, a factor of 10,000 dimmer. That weakness was the first clue that something unusual was going on. Either the jet was intrinsically weak, which would be strange given the energy available in a neutron-star merger, or we were not looking down the barrel. The jet was there, but it was pointed away from us. We were seeing the edge of the beam. The X-ray and radio observations confirmed it. If the jet had been pointed at Earth, the X-ray and radio afterglow should have been bright and should have peaked within a few hours or days. Instead, the X-rays took 2 weeks to become detectable, and the radio emission took a month to reach its peak. That delayed brightening was exactly what models predicted for an off-axis jet. When the jet is not pointed at you, the initial emission is weak because you are not in the beaming cone. But as the jet plows into the surrounding gas, it decelerates. The beaming cone widens. Eventually, it widens enough that Earth enters the cone and the emission brightens. The timescale for that brightening depends on how fast the jet is moving and how much gas it is plowing through. For GW170817, the timescale was weeks. That gave astronomers a way to measure the jet structure and the surrounding environment. The jet was there. It was moving at relativistic speeds, and it was slightly misaligned, pointed maybe 15 or 20 degrees away from our line of sight. The energy budget of a relativistic jet is enormous. The total energy in the jet from GW170817 was estimated at about 10 to the 50 erg. That is 1 followed by 50 zeros in erg. For comparison, the Sun will radiate about 10 to the 50 erg over its entire 10 billion year lifetime. A neutron star merger releases that much energy in the jet alone, and it does it in a few seconds. Add in the gravitational wave energy, the kilonova energy, and the neutrino energy, and the total energy output of the merger is closer to 10 to the 53 erg, about 10% of the total rest mass energy of the system. 10% of 2 solar masses converted entirely into energy and radiated away in less than a minute. That is not fusion. Fusion converts less than 1% of mass into energy. This is gravitational collapse. This is matter falling into a region of spacetime so warped that falling releases energy at efficiencies fusion cannot touch. The particles in the jet are accelerated to extreme energies. Electrons, positrons, protons, all of them get kicked to velocities where their kinetic energy dominates over their rest mass. The Lorentz factor, the ratio of the particle's energy to its rest mass energy, can reach tens or even hundreds. A particle with a Lorentz factor of 10 is moving at roughly 99.5% the speed of light. A Lorentz factor of 100 corresponds to 99.995% the speed of light. These particles are not just fast. They are energetic enough to produce high-energy radiation when they interact with magnetic fields or with photons. As the particles spiral around magnetic field lines, they radiate synchrotron emission, light produced by accelerating charges in a magnetic field. The spectrum of synchrotron emission extends from radio waves all the way up to X-rays and gamma rays, depending on the strength of the magnetic field and the energy of the particles. That synchrotron glow is what telescopes detect as the afterglow of the gamma-ray burst. The jet itself is invisible. What we see is the light produced by jet particles interacting with their environment. The collimation of the jet, the fact that it is narrow rather than a spherical explosion, is a direct consequence of the magnetic field geometry and the rotation of the system. If you just had a hot accretion disk with no magnetic fields, the energy would radiate outward in all directions. You would get a spherical fireball, not a jet. But the magnetic fields break the symmetry. They define a preferred direction, the rotation axis, and they channel the energy along that axis. The jet is not perfectly cylindrical. Models suggest it has structure, a narrow, fast core surrounded by a slower, wider sheath. The core moves at the highest speeds, close to the speed of light, and carries most of the energy. The sheath moves more slowly, perhaps 90% the speed of light, and is less energetic. When the jet is pointed at you, you see the core. When it is off-axis, you see the sheath. That structure explains why some gamma-ray bursts are extremely bright and others are dim. It is not that the jets are fundamentally different. It is that we are looking at them from different angles. The connection between short gamma-ray bursts and neutron star mergers had been suspected for decades. Short bursts, the ones lasting less than 2 seconds, are statistically different from long bursts, which last anywhere from a few seconds to several minutes. Long bursts are associated with the deaths of massive stars, core collapse supernova, where the collapsing core forms a black hole and launches a jet. The evidence for that connection is strong. Long bursts are always found in star-forming regions, places where massive stars are being born and dying. Short bursts are different. They show up in older galaxies where star formation has slowed or stopped. That distribution suggested a different origin, something that does not require recent star formation. Neutron star mergers fit the bill. Neutron stars are born in supernovae, but they can live for billions of years before they merge. A short burst in an old galaxy makes sense if it is coming from a neutron star binary that has been orbiting for eons and finally spiraled in. GW 170817 confirmed it. The gravitational wave signal proved that 2 neutron stars had merged. The gamma-ray burst arrived less than 2 seconds later. The connection was direct. Short gamma-ray bursts are produced by neutron star mergers. Not all of them, necessarily. A neutron star merging with a black hole could also produce a short burst, and the physics would be similar. But neutron star mergers are the primary source. The problem had been solved not by better gamma-ray observations or better theoretical models, but by gravitational waves. By listening to the in-spiral, Astronomers knew exactly what kind of object had produced the burst. No ambiguity. 2 neutron stars, collision, jet, gamma rays, done. The gamma ray burst itself is brief, but the afterglow can last for weeks or months. The jet, moving at close to the speed of light, slams into the gas surrounding the merger site. That gas is not empty space. It is the outer layers of the original binary system, material that was blown off the stars during earlier stages of their evolution, plus any gas that happened to be sitting in the interstellar medium nearby. The jet plows through this material like a bullet through water. The collision heats the gas to extreme temperatures and generates a shock wave that propagates outward. Behind the shock, the gas cools and radiates. That radiation is the afterglow. Early on, the afterglow is dominated by X-rays. As the shock expands and cools, the peak of the emission shifts to lower energies. First optical, then infrared, then radio. The spectrum and the evolution of the afterglow encode information about the jet structure, the density of the surrounding gas, and the magnetic field strength. Astronomers can work backward from the afterglow observations to reconstruct the properties of the jet and the environment it is moving through. For GW 170817, the afterglow observations were extraordinary. Multiple telescopes tracked the X-ray and radio emission for more than a year. The X-rays peaked around 100 days after the merger and then began to fade. The radio emission peaked even later, around 150 days, and then slowly declined. The late peak was a direct signature of an off-axis jet. If the jet had been pointed at us, the emission would have peaked within days. The delayed peak meant the beaming cone was gradually widening as the jet decelerated, and we were watching it come into view. The data allowed astronomers to measure the opening angle of the jet, roughly 15 to 20 degrees, and to estimate the total energy, about 10 to the 50 erg. Those numbers matched the predictions from theoretical models almost perfectly. The physics worked. The models were right. Neutron star mergers produce relativistic jets with opening angles of tens of degrees, kinetic energies of 10 to the 50 erg, and velocities approaching the speed of light. One of the strangest aspects of relativistic jets is the role of time dilation. An object moving at close to the speed of light experiences time more slowly than an object at rest. The faster you move, the slower your clock ticks relative to an outside observer. For a jet moving at 99.9% the speed of light, the Lorentz factor is about 22. That means time on the jet is running 22 times slower than time in the rest frame of the surrounding galaxy. A second on the jet is 22 seconds for everyone else. This has real consequences for what happens inside the jet. Particles that would normally decay in microseconds can survive for much longer in the jet frame because time is stretched. The jet effectively carries its own bubble of slowed time, and anything inside that bubble gets to live longer, move farther, and interact more before decaying or radiating away its energy. The gravitational environment near the remnant is another key piece of the puzzle. Whether the merged object is a hypermassive neutron star or a newborn black hole, the gravitational field is intense. The escape velocity at the surface of a neutron star is about half the speed of light. For a black hole, the escape velocity at the event horizon is exactly the speed of light by definition. Anything trying to leave that environment has to climb out of a deep gravitational well, and doing so costs energy. The jets are powered by the gravitational potential energy of the infalling matter. Gas spiraling into the remnant loses potential energy, and that energy gets converted into heat, radiation, and kinetic energy of the jet. The efficiency of that conversion is high, much higher than fusion or any chemical process. That is why the jets are so powerful. The source is not chemical bonds or nuclear reactions. The source is gravity. Pure space-time curvature, releasing energy as matter falls toward the point of no return. The magnetic fields near the remnant are also extreme. Neutron stars have surface magnetic fields that can reach trillions of Gauss. When two neutron stars merge, those fields get tangled and amplified. The resulting magnetic structure is chaotic, but it is also incredibly strong. Strong enough to dominate the dynamics of the accretion disk, strong enough to channel matter into jets and accelerate particles to relativistic speeds. The exact mechanism is still being worked out, but the basic picture is clear. Magnetic fields extract energy from the spinning remnant, either from the rotation of the neutron star or from the spin of the black hole if the system has already collapsed, and funnel that energy into the jets. The jets are, in a sense, magnetic catapults. They take rotational energy and gravitational energy, wrap them in magnetic fields, and hurl them outward at nearly the speed of light. The orientation of the jet relative to Earth matters enormously for what we detect. If the jet is pointed at us, we see a bright gamma-ray burst and a rapidly fading afterglow. If the jet is pointed away, we see nothing in gamma rays, but we might still detect the kilonova. If the jet is somewhere in between, we see a weak gamma-ray burst and a delayed afterglow. GW170817 was the first time astronomers had the full picture. They knew the masses of the merging stars from the gravitational waves. They knew the distance from the amplitude of the gravitational wave signal. They knew the orientation from the weakness of the gamma-ray burst and the delayed X-ray and radio brightening. And they knew the composition of the ejecta from the kilonova spectroscopy. No single piece of information would have been enough. The gravitational waves without the gamma rays would have told them about the merger, but not about the jet. The gamma rays without the gravitational waves would have told them about the jet, but not about the merger. Together, they painted a complete picture. The jets are not eternal. They last only as long as the accretion disk can feed them, and the disk does not last long. Within a few seconds, most of the available material has either fallen into the remnant or been blown away. The jet shuts off. What is left is the expanding debris, the kilonova ejecta spreading outward, and the fading afterglow as the jet plows through the surrounding gas and eventually dissipates. But for those few seconds, the jet is one of the brightest objects in the universe, brighter than the kilonova, brighter than the host galaxy, brighter in some cases than entire galaxy clusters. The energy output is staggering, and it is all concentrated into a narrow beam only a few degrees wide. If you happen to be standing a few light years away, directly in the path of the jet, you would not survive long enough to appreciate the view. The radiation field would vaporize anything in its path. The discovery of relativistic jets from neutron star mergers has implications beyond just understanding gamma-ray bursts. The jets are probes of the post-merger environment. By studying how the jet interacts with the surrounding gas, astronomers can learn about the density and composition of that gas. By measuring the speed and energy of the jet, they can infer the properties of the remnant. Did it collapse immediately into a black hole, or did it survive as a neutron star for a few seconds? The answer is encoded in the jet. A longer-lived neutron star might produce a different jet structure than an immediate collapse. The details are subtle, but they are measurable. And with more detections, more neutron star mergers observed in both gravitational waves and electromagnetic radiation, astronomers will be able to build a statistical picture of what happens in the first few seconds after the collision. How often does the remnant survive? How often does it collapse? What determines the outcome? The jets are witnesses. They carry information out of the chaos and scatter it across the universe for anyone with a telescope to read. The speed of the jets, 99.9% the speed of light or more, is a testament to the extremity of the environment. You do not accelerate matter to those speeds with a gentle push. You need enormous energy densities, intense magnetic fields, and the kind of gravitational gradients that exist only near the most compact objects in the universe, neutron stars and black holes. The jets are not anomalies. They are not accidents. They are the natural consequence of matter falling into a deep gravitational well while being guided by magnetic fields. The same physics that produces jets from supermassive black holes at the centers of galaxies, jets that stretch for millions of light years, also produces jets from neutron star mergers. The scales are different, the energies are different, but the underlying mechanism is the same. Gravity, rotation, magnetic fields, and a pathway for energy to escape. Point those ingredients at the sky and pull the trigger. Out comes a jet, and that jet, brief and violent as it is the reason we know neutron star mergers happen at all. Before gravitational wave astronomy, before LIGO, the only way to find these events was through gamma-ray bursts. Short bursts were the smoking gun. Now we have two ways to detect them. We can listen for the gravitational waves, and we can watch for the gamma rays. Between the two, we are beginning to understand not just that these events happen, but how they happen. The in-spiral, the merger, the kilonova, the jet, each piece of the story told by a different messenger. Gravitational waves for the masses and the orbit, gamma rays for the jet, optical and infrared for the kilonova, radio and X-rays for the afterglow. Multi-messenger astronomy in action. The universe speaking in every language it knows, and for the first time we are listening to all of them at once. The jets do more than announce the merger. They shape the environment around it. The energy they deposit into the surrounding gas heats it, ionizes it, drives shock waves that can trigger star formation or blow gas out of the galaxy entirely. Over millions of years, the effects of a single neutron star merger can ripple outward, affecting the evolution of the host galaxy in ways we are only beginning to understand. The kilonova contributes heavy elements, the jet contributes energy, both leave their mark. And if you trace the history of a galaxy backward, every neutron star merger it has ever hosted has left fingerprints, some visible, some hidden, but all of them real. The jets are also, in a very literal sense, the closest thing we have to a natural particle accelerator operating at energies we cannot reproduce on Earth. The Large Hadron Collider, the most powerful particle accelerator ever built, smashes protons together at energies of about 10 trillion electron volts. Impressive. But the particles in a relativistic jet can reach energies 1,000,000 times higher, 100 million trillion electron volts. Cosmic rays, the high-energy particles that constantly bombard Earth from space, might be accelerated in environments like this. Neutron star mergers, supernova remnants. Anywhere a shock wave or a magnetic field can grab a particle and fling it to absurd speeds, the jets are laboratories, extreme physics laboratories, and they are running experiments that no human will ever be able to replicate in a controlled setting. The story of the jets is the story of energy conversion, gravitational energy, rotational energy, magnetic energy, all of it funneled into kinetic energy and radiation. The efficiency is terrifying. 10% of the rest mass energy of the merging system gets radiated away. Not over billions of years like a normal star. In seconds. If you could harness that kind of energy conversion, you could power human civilization for longer than it has existed on a fraction of the fuel. But you cannot harness it. The conditions required, the densities, the temperatures, the magnetic fields, are so far beyond anything we can create. that the very idea of building a neutron star merger in a laboratory is absurd. We can only watch, measure, learn, and be grateful that the nearest neutron star binary is thousands of light years away and will not merge for millions of years. Because if one went off next door, the jet would sterilize every planet within a few dozen light years. No warning, just gamma rays, a flash, and silence. The jets connect the merger to the rest of the universe. They are the mechanism by which the collision becomes visible across hundreds of millions of light years. Without the jets, a neutron star merger would be a local event. Gravitational waves, yes. A kilonova, yes. But dim, hard to find, easy to miss. The jets amplify the signal. They turn a merger into a beacon, and in doing so, they give astronomers a way to study these events in detail, to measure the physics, to test the models, to understand what happens when two of the densest objects in the universe collide and produce, for a few brief seconds, some of the most extreme conditions nature allows. The jets are the exclamation point, the announcement, the signal that something extraordinary just happened and the universe is not staying quiet about it. The energy released by the jets, the particles accelerated to near light speed, the gamma rays blasting outward, all of it is part of the same story. A story that begins with two massive stars, continues through two supernovae, and ends with a collision that forges gold, launches jets, and rings spacetime like a bell. The jets are not a side effect, they are part of the main event. And understanding them, measuring them, tracking how they evolve and interact with their surroundings is one of the key goals of modern astrophysics. Because the jets tell you what is happening at the center, where the densities are highest, where the magnetic fields are strongest, where gravity is squeezing spacetime into shapes that barely make sense. The jets are messengers from that environment, and the message they carry is simple. This is what happens when you compress 2 suns worth of matter into a ball the size of a city and then smash it together at close to the speed of light. You get a jet, you get gamma rays, you get an explosion that briefly rivals the brightness of 1 billion stars. And you get, if you are lucky, a front row seat to the most violent events in the cosmos. Which brings us to the question that has been sitting in the background this entire time. The jets produce gamma rays, the kilonova produces light, but both of those are symptoms. The cause, the thing that makes all of this possible, is the collision itself, and the collision does more than launch jets and eject debris. It forges elements, the heaviest elements, elements that cannot be made anywhere else. Gold, platinum, uranium. The cosmic anvil where those elements are hammered into existence is the subject of the next part of this story. How a collision lasting seconds produces enough gold to fill multiple planets. How that gold gets scattered across space. And how, billions of years later, it ends up in your hand. The jets are the announcement, the kilonova is the glow, but neither of those tells you where the gold came from. Not really, because the gold, the platinum, the uranium, all of it existed for exactly 0 seconds before the collision happened. It was not sitting inside the neutron stars waiting to be released. It was not drifting around in space hoping to get swept up. It was made, forged, assembled atom by atom in the chaos of the merger itself, under conditions so extreme that the normal rules of chemistry and nuclear physics bend until they snap. And understanding how that works, how you go from 2 balls of neutrons to a cloud of gold spreading outward at thousands of kilometers per second, requires stepping back, way back, to the beginning. Because the story of gold is also the story of every element heavier than helium. And that story starts with nothing. In the beginning there was hydrogen. That is not poetry, that is cosmology. The universe in its first few minutes was hot enough and dense enough for nuclear fusion to occur everywhere at once. Protons, the nuclei of hydrogen atoms, slammed into each other and fused into helium. Some of that helium fused further into lithium. A tiny amount of beryllium formed and immediately decayed. And then the universe expanded and cooled, and fusion stopped. 3 minutes. That is how long Big Bang nucleosynthesis lasted. 3 minutes of furious fusion, and then silence. What came out the other side was a universe that was roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium and essentially nothing else. No carbon, no oxygen, no iron, no gold. Just the two lightest elements and a faint whisper of the third. That composition held for hundreds of millions of years. The universe expanded. It cooled. The hydrogen and helium drifted through space, slowly clumping together under the pull of gravity. Dark matter, which does not interact with light but does interact gravitationally, provided the scaffolding. Gas collected in the densest regions, forming clouds that grew larger and denser until eventually they collapsed. The first stars ignited. Population 3 stars, astronomers call them, though no one has ever seen one directly. They were massive, hundreds of times the mass of the Sun in some cases, and they were made entirely of hydrogen and helium. No heavy elements at all. That affects the physics. Without heavy elements, gas clouds cool less efficiently, so the fragments that collapse into stars are larger. The first stars were giants. And giants burn fast. A star like our Sun fuses hydrogen into helium in its core. The process is slow. Our Sun has been burning for about 4.5 billion years and will continue for another 5 billion. It fuses hydrogen at a rate that converts about 4 million tons of mass into energy every second, and even at that rate, it has only burned through about half of its hydrogen supply. The first stars, the population 3 giants, were not so patient. They burned hydrogen into helium at a ferocious rate, exhausted their fuel in a few million years, and then moved on to the next stage, helium fusion. Helium nuclei, 2 protons and 2 neutrons each, fuse together to form carbon. 3 helium nuclei fuse to form oxygen. The core contracts. The temperature rises. Carbon fuses with helium to form oxygen and neon. Oxygen fuses to form magnesium and sulfur. Neon fuses, silicon fuses. Each stage runs faster than the one before it because the energy yield per fusion reaction drops as you move up the periodic table. By the time the core is fusing silicon into iron, the star has only days left to live, maybe hours. Iron is the end of the line. Fusing iron into anything heavier does not release energy. It costs energy. The nucleus of an iron atom, 26 protons and roughly 30 neutrons, is the most stable configuration in the universe. Splitting it or fusing it both require an input of energy rather than producing energy. Stars are in the business of producing energy, so when the core turns to iron, fusion stops. The outward pressure that had been holding the star up against its own weight vanishes. The core collapses. The outer layers fall inward, and then the core, now compressed into a ball of neutrons, rebounds. The outer layers, falling inward at a quarter of the speed of light, hit the rebounding core and explode. Supernova. The explosion is violent enough to briefly outshine an entire galaxy. And in the chaos, in the shock wave tearing through the star's outer layers, some heavy elements are made. Supernovae can produce elements up to and slightly beyond iron. The explosion generates intense heat and a flood of neutrons, and in that environment, nuclei can capture neutrons and build up into heavier elements. But the process is limited. The explosion lasts only a few seconds. The neutron density is high, but not absurdly high. and the conditions are chaotic. The result is that supernovae can make elements like nickel, cobalt, copper, zinc. They can even make small amounts of heavier elements like silver and tin through a process called the C process, slow neutron capture, which happens in the outer layers of certain aging stars before they explode. But the C process stops around lead. It cannot build the heaviest elements. It cannot make gold in significant quantities. It cannot make platinum or uranium at all. For those, you need something else. You need the free process, rapid neutron capture. The free process requires three things. First, an extreme neutron density. You need so many free neutrons that when a nucleus sits in that environment, it is constantly being bombarded. Neutrons stick to the nucleus faster than the nucleus can decay. Second, high temperature. The neutrons need enough energy that when they collide with a nucleus, they actually get absorbed rather than just bouncing off. Third, rapid expansion. The neutron-rich environment cannot last long. If it does, the neutrons decay into protons and the process stops. You need the whole thing to run for a few seconds, build up heavy nuclei, and then freeze out. Let the unstable nuclei decay into stable forms while the material cools and expands. For decades, astronomers debated where that process happens. Supernovae were the obvious candidate. The explosion provides heat and neutrons. But the conditions inside a supernova are extraordinarily complicated, and it was never clear that the neutron density was high enough in the right place at the right time. Some simulations said yes, others said no. The models disagreed, and there was no direct observational evidence either way. Nobody had ever caught a supernova in the act of making gold. The idea lingered as a possibility, but it was never confirmed. Then in 2017, gravitational wave detectors heard a neutron star merger. Telescopes saw the kilonova, and the spectrum of the kilonova, the light it was emitting, was consistent with a cloud of debris rich in heavy reprocess elements, gold, platinum, everything the R process predicts. The case was closed. Neutron star mergers make the heaviest elements, not supernovae, not exclusively anyway. The main factory is neutron star collisions. Here is why. When two neutron stars collide, they do not just merge cleanly into a single object. The collision is violent. The outer layers of both stars, material that is not quite dense enough to stay bound to the core, gets flung outward. The debris is neutron-rich, extraordinarily neutron-rich. Neutron stars are made almost entirely of neutrons, so the ejected material has a neutron-to-proton ratio that is far higher than anything you would find in normal matter. That is exactly what the R process needs. The debris is also hot, billions of degrees, heated by the violence of the collision, and it is expanding rapidly, thousands of kilometers per second, so the neutron-rich phase lasts only a few seconds before the material thins out and cools. Those few seconds are enough. Seed nuclei in the debris, things like iron or nickel, start capturing neutrons, one after another. The nucleus gets heavier and heavier, piling on neutrons faster than it can decay. Eventually, the nucleus is so neutron-rich that it cannot hold together anymore, and it undergoes fission, splitting into smaller pieces. But before that happens, you have built a very heavy, very neutron-rich nucleus. Once the neutron flood stops, the nucleus starts decaying, beta decay. Each neutron turns into a proton, an electron, and an antineutrino. The nucleus climbs up the periodic table, shifting from one element to the next, until it reaches a stable configuration: gold, platinum, uranium, whatever the decay chain leads to. The amount of heavy elements produced in a single neutron star merger is staggering. The best estimates, based on observations of the 2017 Kilonova and theoretical models of R-process nucleosynthesis, say that a typical merger ejects somewhere between 1/100th and 1/10th of a solar mass of material. Most of that material is in the form of heavy elements. The neutron-to-proton ratio is so extreme that nearly everything ends up heavier than iron. A few hundredths of a solar mass is roughly 10 to 100 Earth masses. One merger, tens of Earth masses of heavy elements, and a significant fraction of that is gold. The exact percentage depends on the details of the R process, the temperature, the neutron density, the expansion rate, but the consensus is that gold makes up something like 10 parts per million of the ejecta by mass. 10 parts per million of 10 Earth masses is 1/10th of an Earth mass of gold. 100,000 trillion kilograms of gold, produced in a few seconds, scattered into space at thousands of kilometers per second. That number is so large that it is hard to grasp. For context, all the gold ever mined by humans in recorded history, every gold coin, every piece of jewelry, every gold bar sitting in a vault somewhere, adds up to about 200,000 tons. A single neutron star merger produces roughly 1 billion times that much. Spread it evenly across a sphere 10 light-years in radius, and the density is still high enough that if you could somehow scoop up a cubic kilometer of space, you would find several kilograms of gold mixed in with the hydrogen and helium and other debris. Not concentrated, not in nuggets, just atoms, individual gold nuclei drifting through the expanding cloud. But atoms add up, and over millions of years, as the debris spreads and mixes with the surrounding interstellar gas, those atoms become part of the raw material for new stars and planets. The solar system formed about 4.5 billion years ago from a collapsing cloud of gas and dust. That cloud, the solar nebula, was enriched with heavy elements from previous generations of stars and stellar explosions. Some of those heavy elements came from supernovae. Some came from neutron star mergers. We do not know the exact mix, but the abundance patterns, the relative amounts of different elements we see in the Sun and in meteorites, match the predictions for a combination of S-process and R-process nucleosynthesis. The S-process, which happens in aging giant stars, produces elements up to lead. The R-process, which happens in neutron star mergers, produces the heaviest elements, including gold, platinum, and uranium. The fact that we see both in the solar system means the gas that formed the Sun was enriched by both kinds of events. Multiple supernovae over billions of years, scattering carbon and oxygen and iron into space, and at least a few neutron star mergers, scattering gold and platinum and uranium. The timing matters. Neutron star mergers are rare. A galaxy like the Milky Way probably hosts one every 10,000 to 100,000 years. That sounds like a lot over the 10 billion year history of the galaxy, but it is still far less frequent than supernovae, which happen once every few decades. The result is that the heavy elements from neutron star mergers get diluted. They mix with the much larger amount of lighter elements from supernovae and other sources. By the time the solar nebula collapsed, the concentration of gold in the gas was tiny, a few parts per billion by mass, but tiny is enough. A few parts per billion of the mass of the solar system, which is about 2 × 10⁻30 kilograms, is still a lot of gold. Enough to build a planet with a core that contains more gold than humanity will ever mine. Earth formed hot. The planet was molten, heated by the energy of countless collisions as smaller bodies smashed together and merged. In that molten state, heavy elements like gold and platinum, which are dense and have a strong affinity for iron, sank toward the center. They dissolved into the iron-rich core and stayed there. Most of Earth's gold is still in the core, unreachable, locked away beneath 3,000 kilometers of solid and molten rock. The gold we find in the crust, the gold we mine, is only a tiny fraction of the planet's total inventory. Estimates vary, but the best guess is that Earth's crust contains something like 10 billion tons of gold. That sounds like a lot, until you realize that the core probably contains 1,000 times more, 100 trillion tons or more, sitting there, doing nothing, inaccessible. The gold in the crust got there in a few ways. Some of it never made it to the core during the planet's formation. It stayed in the mantle, the thick layer of rock between the crust and the core, and over billions of years, geological processes brought traces of it to the surface. Volcanic activity, hydrothermal vents, plate tectonics, all of these processes move material from deep inside the Earth to the surface, and some of that material carries gold. The concentrations are low, but they are enough to form deposits that humans can mine. Other gold arrived later, delivered by asteroid impacts. After Earth formed and cooled, the planet was bombarded by leftover debris from the solar nebula. Asteroids and comets. Some of those objects contained gold, and when they hit the Earth, they deposited their cargo on the surface. The Late Heavy Bombardment, a period about 4 billion years ago when the inner solar system was pummeled by impacts, likely delivered a significant amount of gold and other heavy elements to Earth's crust. That gold did not sink to the core because the planet had already cooled and solidified. It stayed on the surface, mixed into the rock, waiting for geological processes or human miners to concentrate it into veins and nuggets. The gold you see in jewelry, in electronics, in dental fillings, in investment bars, all of it came from the crust. All of it was mined from the top few kilometers of the planet, and all of it, every atom, was made in a neutron star merger. Not this solar system, not recently. Billions of years ago, in some distant galaxy, two neutron stars spiraled together, collided, and produced a cloud of debris that included the gold now sitting in a ring on someone's finger. That gold drifted through space for hundreds of millions of years. It mixed with gas from other supernovae and other neutron star mergers. Eventually, it became part of a collapsing gas cloud that formed a new star system. That system might have lived and died, scattering the gold back into space. Or the gold might have been incorporated into a planet that was later destroyed in a collision. Either way, the gold kept moving. It drifted through the galaxy, recycled over and over, until finally it ended up in the solar nebula. From there, it became part of Earth. And from Earth, humans dug it up, melted it down, and turned it into currency, art, and technology. The same story applies to every heavy element. Platinum in catalytic converters, turning exhaust fumes into less harmful gases. Uranium in nuclear reactors, splitting atoms and releasing energy. Tungsten in light bulb filaments and drill bits. Lead in batteries and radiation shielding. Every single one of these elements was made in a neutron star merger. There is no other source that works. Supernovae cannot do it. Normal stellar fusion stops at iron. The only process that builds the heaviest elements is the R process, and the only place the R process runs efficiently is in the debris from a neutron star collision. Which means the universe has been running this process over and over for billions of years. Neutron stars form in supernovae. They orbit each other, they spiral inward, they merge, they eject debris. The debris spreads, it mixes, it gets incorporated into new stars. Those stars form planets. Some of those planets develop life. And that life, if it becomes intelligent, eventually figures out that it is made of recycled star guts and neutron star collision debris. We are not just made of star stuff, the famous Carl Sagan line. We are made of Kilonova remnants. Every heavy element in your body, the iodine in your thyroid, the iron in your blood, the calcium in your bones, came from stars. But the heaviest elements, the ones that require the most extreme conditions to form, came from neutron-star mergers. You are walking around with atoms inside you that were forged in collisions so violent they briefly outshone entire galaxies. That is not a metaphor. That is atomic accounting. Then, in 2025, another wrinkle appeared. A team of astronomers analyzing archival data from multiple telescopes found evidence that magnetar flares, giant eruptions of energy from highly magnetized neutron stars, might also produce heavy elements through the array process. Magnetars are neutron stars with magnetic fields so strong that they warp the structure of space itself. Occasionally, those magnetic fields become unstable and snap, releasing an enormous burst of energy. A magnetar flare can release as much energy in 1/10 of a second as the sun will produce in 100,000 years. That energy heats the surface of the neutron star, and some of the surface material gets ejected into space. The material is neutron-rich, just like the debris from a neutron star merger. And if the conditions are right, the ray process can run in that ejected material. The amount of heavy elements produced in a single magnetar flare is much smaller than a neutron star merger, maybe 1/millionth of a solar mass instead of 100th. But magnetar flares are more common than mergers. A magnetar might flare dozens or hundreds of times over its lifetime. And there are a lot of magnetars in the galaxy. Add it all up, and the contribution could be significant. The 2025 analysis suggested that magnetar flares could account for up to 10% of the heavy elements in the galaxy, not the majority. Neutron star mergers are still the main source, but 10% is not nothing. It means the origin story is more complicated than a single process. The universe has multiple factories for making gold. Neutron star mergers are the big ones. Magnetar flares are the side hustle. Together, they explain where the heavy elements came from. The philosophical implications are hard to avoid. Every culture on Earth that has worked with gold, and that is most of them, has treated it as something special, rare, precious, a symbol of wealth and power. Empires have risen and fallen over access to gold. Wars have been fought. People have died. And the entire time the gold itself was just sitting there inert, doing nothing but reflecting light in a way that human brains find appealing. But knowing where the gold came from adds a layer. It was made in a collision between two dead stars. It drifted through space for billions of years. It survived the formation of the solar system. It sank into Earth's core, and some of it was brought back to the surface by geological processes or asteroid impacts. And then humans found it, dug it up, and decided it was valuable. The value is arbitrary. The rarity is not. There is not that much gold in the universe because neutron star mergers are rare and the R process only produces so much per event. The scarcity is cosmological, built in. A consequence of the fact that making heavy elements requires the most extreme conditions nature allows, and those conditions do not happen often. There is also something humbling about the timescale. The gold in a ring made yesterday contains atoms that are older than the Earth, older than the Sun, billions of years old. Those atoms were made in a galaxy that might not even exist anymore. The stars that produced them are long dead. The neutron stars that collided and forged the gold were themselves the remnants of even older stars. The timeline stretches back and back, layer upon layer of stellar evolution and destruction, until you reach the first generation of stars in the universe. Population 3. The ones that had no heavy elements at all. Every heavy element in the universe today is the product of stellar death. Stars live, they burn, they die, and in dying they scatter their ashes into space. Those ashes become the raw material for new stars, new planets, new life. The cycle has been running for more than 10 billion years, and every time you pick up a piece of gold or platinum or any other heavy element, you are holding a piece of that cycle. A fragment of a story that started in the early universe and is still unfolding. The connection between neutron star mergers and the gold on Earth is direct, not symbolic, not poetic, direct. The atoms were made there. They ended up here. The chain of events is traceable. Neutron stars form. They orbit. They merge. They eject debris. The debris spreads. It mixes. It gets pulled into new star-forming regions. It becomes part of planets, and on at least one planet in one solar system, in one galaxy, that debris was concentrated enough and accessible enough that the planet's dominant species started digging it up and using it. We did not create the gold, we just found it. And now, thanks to gravitational wave astronomy and multi-messenger observations, we know where it came from. The 2017 Kilonova was not just a discovery, it was a confirmation. Neutron star mergers make the heavy elements, all of them, the gold, the platinum, the uranium, everything heavier than iron that is not made in supernovae, came from events like that one. And every time a neutron star merger happens anywhere in the universe, more gold is made, more platinum, more of the heaviest elements, scattered into space, waiting. Someday, billions of years from now, some of that newly made gold will be incorporated into a star system that has not even begun to form yet. And maybe, on a planet in that system, something will dig it up and wonder where it came from. The cycle continues. The 2017 detection gave astronomers a way to estimate the rate of heavy element production in the universe. One merger, producing tens of Earth masses of gold, happening once every few tens of thousands of years per galaxy. Multiply that by the number of galaxies in the observable universe, about 2 trillion, and you get a production rate that matches the observed abundance of heavy elements. The math works. Neutron star mergers happen often enough and produce enough heavy elements per event to explain where all the gold in the universe came from. There is no missing source, no mysterious process that has yet to be discovered. The picture is complete. Stars make the light elements. Supernovae make the medium-heavy elements. Neutron star mergers make the heaviest elements. And magnetar flares contribute a small but non-negligible amount. Together, these processes explain the entire periodic table. Hydrogen and helium from the Big Bang, everything else from stars and stellar explosions. The universe is a chemistry lab, and the experiments have been running for more than 13 billion years. And yet, for all the answers the 2017 event provided, there are still mysteries. The gamma-ray burst was weaker than expected. The kilonova was brighter in the first few hours than some models predicted. The X-ray and radio afterglow peaked later than theory said it should. The details do not quite line up, which means the models are missing something. Maybe the jet structure is more complicated than we thought. Maybe the ejector is not spherical symmetric. Maybe there are multiple components, fast ejector from the initial collision and slower ejector from the accretion disk that forms around the remnant. The observations are rich enough that they are starting to reveal the complexity, and that complexity is pointing toward the next set of questions. Not just what happens during a neutron star merger, but what happens after. Does the remnant collapse immediately into a black hole? Does it survive as a hypermassive neutron star for a few seconds before collapsing? What determines the outcome? And what does the remnant look like in the moments before it disappears? Those questions cannot be answered by looking at the light or the gravitational waves alone. They require both, and they require more detections, more neutron star mergers observed from different angles, at different distances with different masses. The 2017 event was the first. It will not be the last, and every new detection will add another piece to the puzzle. The 2017 detection answered one of the biggest questions in astrophysics. Where does the gold come from? Neutron star mergers. Done. Case closed. Nobel Prize material, but science does not work by closing cases and walking away. It works by opening new ones. And GW170817, for all the answers it provided, for all the mysteries it solved, left behind a trail of new questions that astronomers are still trying to answer. The biggest one, the one that keeps theorists awake at night, is also the simplest to state. What happened to the thing that was left behind? When two neutron stars merge, they do not just vanish, they combine. The collision produces a single object, and that object has to be something. The question is what? The two stars that merged in GW170817 weighed roughly 1.4 and 1.3 solar masses. Add them together and you get 2.7 solar masses, give or take. That total mass matters enormously because it determines the fate of the remnant. If the combined mass is below a certain threshold, the merged object might survive as a single massive neutron star. If the mass is above the threshold, the object collapses immediately into a black hole. The threshold itself depends on the equation of state of neutron star matter, the relationship between pressure and density inside a neutron star, and that equation of state is one of the biggest unsolved problems in nuclear physics. We do not know it. We have models, we have guesses, but we do not have the answer. Which means we do not know what happened to the remnant of GW170817, the gravitational wave signal cut off at the moment of merger. That is not surprising. Once the two objects touch and combine, the dynamics become so complicated that the gravitational wave emission changes character. The clean chirp, the rising frequency sweep that LIGO and Virgo detected so clearly, stops. What comes after is much harder to interpret. If the remnant survived as a neutron star, even briefly, it would have been spinning furiously hundreds of times per second, and that spin should produce gravitational waves. But those waves are much weaker and much harder to detect than the in-spiral signal. LIGO's sensitivity was not high enough to pick them up from a source 130 million light-years away. So the gravitational wave data stopped at the merger. Everything after that is inference. The electromagnetic observations do not settle the question either. The gamma-ray burst arrived less than 2 seconds after the merger. That tells you a jet formed quickly, but it does not tell you whether the central object was a neutron star or a black hole when the jet launched. Both scenarios can produce jets. A rapidly spinning neutron star with a strong magnetic field can channel matter along its poles and launch a jet. A black hole surrounded by an accretion disk can do the same thing. The jet alone is not enough to distinguish between the two. The Kilonova light curve, the way the brightness evolved over time, gives some clues. The amount of ejected material, the speed of the ejector, the composition, all of those feed into models that try to reconstruct what happened at the center. But the models are not unique. You can fit the same light curve with different assumptions about the remnant. A black hole that forms immediately ejects material differently than a hypermassive neutron star that survives for a few seconds before collapsing. But the differences are subtle, and the uncertainties in the observations are large enough that both scenarios remain plausible. A hypermassive neutron star is exactly what it sounds like. A neutron star that is too massive to be stable under normal conditions, but is temporarily held up by something other than degeneracy pressure. Rotation helps. A rapidly spinning object experiences centrifugal forces that push outward and partially counteract gravity. Thermal pressure helps too. The remnant is extraordinarily hot, billions of degrees, and that heat creates pressure that resists collapse. Between rotation and thermal support, a hypermassive neutron star can survive for seconds, maybe minutes, before it loses enough angular momentum or cools enough that collapse becomes inevitable. Once that happens, it is over. The object crosses its own event horizon and becomes a black hole. No warning, no second chance, just collapse. The question of how long a hypermassive neutron star can survive matters for a lot of reasons. If the remnant survives even for a few seconds, it has time to do things. It can spin down, radiating energy in gravitational waves and electromagnetic radiation. It can power a jet. It can affect the properties of the ejector, heating some of it, blowing some of it away, changing the composition. All of that feeds back into the kilonova signal. A longer-lived remnant produces a different kilonova than an immediate collapse. The light curve is brighter early on because the remnant is pumping energy into the surrounding material. The spectrum is different because the heating changes which layers of the ejector are visible at which times. Measuring those differences, if you can, tells you how long the remnant survived. But the measurements are hard, the differences are small, and the models are complicated enough that you can adjust other parameters to compensate. It is a degeneracy problem. Multiple sets of assumptions fit the same data. This is the missing link, the transition from neutron star to black hole. We know neutron stars exist. We have observed thousands of them. Pulsars, magnetars, neutron stars in binary systems. They are real. We know black holes exist. We have observed dozens of stellar mass black holes and a handful of supermassive black holes. They are real too. But we have never observed the moment when one turns into the other. We have never caught a neutron star in the act of collapsing. GW170817 was the closest we have come, and it still was not close enough. The gravitational wave signal ended at the merger. The electromagnetic observations started a few seconds later. Everything in between, the critical window where the remnant either survived or collapsed, is hidden. A gap in the data, a blind spot. Future detections will help. The more neutron star mergers we observe, the better we can constrain the models. If every merger shows a similar pattern, that tells you something. If some mergers show different patterns, that tells you something else. Variability is information. And as gravitational wave detectors get more sensitive, they will be able to pick up the post-merger signal, the gravitational waves from the spinning remnant if it exists. That signal is the smoking gun. If you detect it, you know the remnant survived. If you do not, either the remnant collapsed immediately or the signal was too weak to detect. Either way, you learn something. The next generation of detectors, LIGO Voyager, the Einstein telescope, the Cosmic Explorer, will have the sensitivity to do this. They will be able to hear neutron star mergers out to billions of light years and pick up the post-merger oscillations that tell you what the remnant is doing in those first few seconds. That is when the missing link stops being missing. Then there is the R process itself. The 2017 Kilonova confirmed that neutron star mergers produce heavy elements. The spectral signatures, the color evolution, the total luminosity, all of it matched the predictions for R process nucleosynthesis. But the models are still rough. The R process is absurdly complicated. You are tracking thousands of different isotopes, each with its own decay chain, each interacting with neutrons at different rates depending on the temperature and density. The nuclear physics is cutting edge. Some of the isotopes involved have never been created in a laboratory. Their properties, their masses, their decay modes are estimated from theory rather than measured directly. That introduces uncertainty. The models can tell you roughly how much gold you should get, and roughly what the isotopic composition should be, but the details are fuzzy, and the details matter because the details encode information about the conditions in the ejector, the temperature, the density, the neutron-to-proton ratio, how fast the material is expanding. All of that affects which isotopes form and in what abundances. The only way to sharpen the models is to get better data, more kilonovae, more spectroscopy, detailed measurements of the light curves in multiple wavelengths, not just optical and infrared, but ultraviolet and near-infrared and mid-infrared. Each wavelength probes a different part of the ejector, a different temperature range, a different set of elements. Combine them, and you can start to map the structure of the debris cloud. Which layers are moving fastest? Which layers are richest in heavy elements? How the composition changes with time as the cloud expands and cools. That information feeds back into the Sri process models and lets you test whether the nuclear physics is right. If the models predict the wrong isotope ratios, that tells you something is off. Maybe the neutron capture rates are wrong. Maybe the fission probabilities are wrong. Maybe there is a nuclear process we have not accounted for. Either way, you learn, and over time, as the models get better and the observations get sharper, the picture converges. We are not there yet, but we are getting closer. Another piece of the puzzle is the diversity of the events themselves. GW170817 was one merger, one data point. And it was unusual in several ways. The gamma-ray burst was weak. The viewing angle was off-axis. The total mass of the system, 2.7 solar masses, was right on the edge of the threshold for immediate collapse. What happens if you change the parameters? What if the neutron stars are more massive? What if the viewing angle is different? What if the equation of state is stiffer or softer? Each variation produces a different signal, a different kilonova light curve, a different gamma-ray burst, a different gravitational wave signature. The challenge is to observe enough mergers that you can map out that parameter space, find the patterns, figure out which properties are universal and which depend on the details. Short gamma-ray bursts are part of that picture. Before GW170817, astronomers knew that short gamma-ray bursts existed. They had been detecting them since the late 1960s, but they did not know what caused them. The leading theory was neutron star mergers, but it was just a theory, no proof. GW170817 provided the proof. Short gamma-ray bursts come from neutron star mergers, at least some of them, but not all short bursts are the same. Some are brighter than others, some last longer, some have extended emission that continues for tens of seconds after the initial spike. The diversity suggests that the mergers themselves are diverse, different masses, different spins, different magnetic field strengths, different amounts of ejector. All of that affects what you see. The burst from GW170817 was on the faint end of the distribution. That makes sense if the jet was pointed away from us. But there are other faint bursts in the catalogue that might also be off-axis events, and there are bright bursts that are probably on-axis. By studying the full population, comparing the bursts to the gravitational wave detections when both are available, astronomers can start to build a statistical picture. How often do neutron stars merge? What is the typical mass ratio? How often does the remnant collapse immediately versus surviving for a few seconds? How much heavy element production do you get per event? Those are population-level questions, and answering them requires a large sample. One event is not enough. 10 might be. 100 definitely is. The diversity extends to the kilonovae as well. At 2017 GFO, the Kilonova from GW170817 was the first one ever clearly identified. But astronomers have gone back through archival data and found hints of other kilonovae associated with short gamma-ray bursts. The signals are faint and the data are sparse, but the patterns are there. Some kilonovae are bluer, some are redder, some fade faster. The variations tell you about the ejector. A blue kilonova means the ejector is dominated by lighter process elements, things like strontium and zirconium. A red kilonova means the ejector is rich in the heaviest elements, gold and platinum and beyond. The color tells you the composition, the brightness tells you the mass, the duration tells you the expansion speed. Every kilonova is a snapshot of a different merger under slightly different conditions. The more snapshots you collect, the clearer the overall picture becomes. One of the surprises from the 2017 event was how bright the kilonova was in the first few hours. Some of the early models predicted a much dimmer initial peak. The brightness suggested that there was additional heating, something beyond just radioactive decay of our process elements. One possibility is that the remnant survived as a hypermassive neutron star for a few seconds and pumped extra energy into the ejector before collapsing. Another possibility is that the ejector has multiple components: fast material from the initial collision and slower material from the accretion disk that forms afterward. The fast material would produce the early blue peak. The slow material, richer in heavy elements, would produce the later red emission. Both components contribute to the total light curve, and the balance between them depends on the details of the merger. Sorting this out requires better models and more data. But the basic message is clear. Kilonovae are not simple. They have structure, layers, and understanding that structure is key to understanding the merger. Then there is the future. The field of gravitational wave astronomy is barely a decade old. LIGO made its first detection in 2015. The first neutron star merger was detected in 2017. In less than 10 years, the field has gone from 0 detections to routine observations of black hole mergers and a handful of neutron star events. The next 10 years will be transformative. LIGO and Virgo are being upgraded. The detectors will get more sensitive, roughly doubling their range with each upgrade cycle. That means the volume of space they can survey grows by a factor of 8. More volume means more detections. The current generation of detectors picks up a few neutron star mergers per year. The next generation will pick up dozens, maybe hundreds. New detectors are being built. LIGO India, a third LIGO detector under construction in India, will join the network and improve the ability to localize sources on the sky. Better localization means faster follow-up with optical and radio telescopes. Faster follow-up means catching the kilonova while it is still bright. Kagra, the Japanese detector, is already online but is still being upgraded to reach its design sensitivity. Once it does, the global network will have 4 detectors running simultaneously, giving even better sky coverage and localization. Beyond that, there are plans for next-generation ground-based detectors. The Einstein telescope, a proposed European detector with arms 10 kilometers long, 3 times the length of LIGO's arms. The Cosmic Explorer, a proposed US detector with arms 40 kilometers long. These instruments will be so sensitive that they will detect neutron star mergers across the entire observable universe. Every merger that happens anywhere will be detectable, assuming the signal is strong enough. The event rate will go from a few per year to thousands per year. And then there is space. Ground-based detectors are limited by seismic noise and other sources of vibration. They cannot detect gravitational waves at frequencies below about 10 Hz because the ground itself is too noisy. But some of the most interesting sources, things like supermassive black hole mergers and extreme mass ratio in spirals where a small black hole spirals into a supermassive one, produce gravitational waves at much lower frequencies, millihertz. To detect those, you need a space-based detector. LISA, the Laser Interferometer Space Antenna, is scheduled to launch in the 2030s. It will consist of 3 spacecraft flying in formation, separated by millions of kilometers, using laser beams to measure the distances between them. LISA will open an entirely new window on the gravitational wave universe, detecting sources that ground-based instruments cannot see, including, potentially, the inspiral of intermediate mass black holes, or the mergers of black holes in the centers of distant galaxies. LISA will not detect neutron star mergers, the frequency is wrong, but it will detect other things, and those other things will fill in more pieces of the puzzle. How black holes grow, how galaxies evolve, how the early universe behaved in its first few 100 million years. All of that from gravitational waves. The promise of multi-messenger astronomy is that it gives you more information than any single messenger can provide. Gravitational waves tell you the masses and the orbit. Electromagnetic observations tell you the composition and the environment. Neutrinos, if you can detect them, tell you about the core. Each messenger probes a different aspect of the event, and together they give you a complete picture. The 2017 event was proof of concept, the first time humanity observed a cosmic event using multiple messengers simultaneously. It will not be the last. The infrastructure is in place. The detectors are running. The coordination between gravitational wave astronomers and electromagnetic observers is routine now. When LIGO or Virgo detects a neutron star merger, alerts go out within seconds to telescopes all over the world. Observers swing into action, searching for the optical counterpart, the Kilonova. When they find it, follow-up observations begin: spectroscopy, photometry, monitoring the evolution over days and weeks. The whole process is coordinated and automated to a degree that would have been unthinkable 20 years ago, and it works. GW170817 proved it works. The next step is to make it better. Faster alerts, more sensitive detectors, better localization so that optical telescopes do not have to search such large areas of sky, improved models so that theorists can predict what observers should be looking for. The tools are improving, the techniques are being refined, and the science is accelerating. Within a decade, neutron star mergers will go from rare exotic events to well-studied phenomena with large statistical samples. The questions that remain open today, the fate of the remnant, the details of the rare process, the diversity of kilonovae and gamma-ray bursts, will have answers, not complete answers necessarily. Science never finishes, but better answers, sharper answers, answers that constrain the models tightly enough that the remaining uncertainties are small. One of the most exciting prospects is the ability to use neutron star mergers as probes of fundamental physics. The equation of state of neutron star matter is one example. It determines the maximum mass a neutron star can have before collapsing into a black hole. It determines how stiff or soft the star is, how much it resists being compressed, and it is intimately connected to the behavior of nuclear matter at densities higher than anything we can create in a laboratory. By observing enough neutron star mergers, measuring the masses of the merging stars, tracking what happens to the remnant, astronomers can map out the equation of state. Each detection adds a data point. Each data point narrows the range of possibilities. Eventually, the equation of state will be known well enough that it can be compared directly to theoretical predictions from quantum chromodynamics, the theory of the strong nuclear force. That is a bridge between astrophysics and particle physics, two fields that do not normally talk to each other much, connected by the deaths of neutron stars. Neutron star mergers also provide tests of general relativity. The 2017 event tested whether gravitational waves and light travel at the same speed they do to within 1 part in 10 to the 15th. That is an absurdly tight constraint, and it ruled out a number of alternative theories of gravity that predicted even tiny differences. Future mergers will test other aspects of general relativity: the way spacetime behaves near the point of collision, the structure of the gravitational wave signal as the two objects spiral together, the ring-down after the merger, the way the newly formed black hole settles into its final state. Every piece of the waveform encodes information about how gravity works at extreme conditions. Conditions where the curvature of spacetime is so strong that Newtonian physics breaks down completely and even general relativity is being pushed to its limits. If there are deviations from Einstein's predictions, this is where they will show up. So far, every test has confirmed general relativity. The theory keeps passing, but the tests keep getting sharper, and eventually, if there is new physics hiding in the strong field regime, we will find it. There is also the question of how common these events are in the history of the universe. Neutron star mergers happen now in the local universe at a rate of a few per year in a volume containing millions of galaxies. But what about the past? The rate of neutron star mergers depends on the rate of star formation, because neutron stars are born in supernovae, and supernovae come from massive stars. The star formation rate in the universe peaked about 10 billion years ago and has been declining since. That means the neutron star merger rate was probably higher in the past than it is today. How much higher? Nobody knows for sure. But if the rate was high enough, neutron star mergers could have played a major role in enriching the early universe with heavy elements. The first galaxies, the ones that formed a billion years after the Big Bang, already contained heavy elements. We know because we can see absorption lines in the spectra of distant quasars, and those absorption lines come from gas clouds that contain carbon, oxygen, silicon, iron, and even some R-process elements. Where did those elements come from? The first generation of stars, population 3, made some of them, but population 3 stars were pure hydrogen and helium. They had no heavy elements to start with. Everything they made had to come from fusion and supernovae do not make much in the way of re-process elements. Neutron star mergers do. If enough mergers happened early enough, they could have seeded the early universe with gold and platinum and uranium. That material would have been incorporated into the next generation of stars, spreading the heavy elements through the galaxy. Over billions of years, the cycle repeated. Stars formed, stars died, neutron stars merged. The galaxy got richer in heavy elements, and eventually one of those stars was our Sun, and one of the planets around that star was Earth. And on that planet, something evolved that could look up at the sky and ask where the gold came from. The answer, it turns out, was written in the collisions of dead stars. The 2017 event was a turning point. It confirmed that neutron star mergers happen. It confirmed that they produce heavy elements. It confirmed that they produce short gamma-ray bursts. It confirmed that gravitational waves travel at the speed of light. It gave astronomers the first direct look at the R process in action. And it opened the door to multi-messenger astronomy, the ability to study cosmic events using every available type of observation. That door is not closing, it is widening. The detectors are getting better, the techniques are improving. The coordination between different branches of astronomy is tighter than ever, and the science is accelerating. But for all the progress, the biggest questions remain open. What happens to the remnant in the seconds after the merger? Does it survive as a hypermassive neutron star or collapse immediately into a black hole? How does the R process work in detail? Which nuclear reactions dominate? How do the isotopic abundances depend on the temperature and density? How diverse are kilonovae? How much does the signal depend on the mass ratio of the merging stars, the spin, the magnetic field strength? How often do neutron star mergers happen in the universe, and has the rate changed over cosmic time? How much of the heavy element budget comes from mergers versus other sources like magneta flares or rare types of supernovae? These are not easy questions. They require more data, more detections, more detailed observations, and they require better models, tighter integration between theory and observation, and a willingness to let the data challenge assumptions that have been around for decades. The missing link, the gap between neutron star and black hole, is the sharpest example. We know both objects exist. We know one can turn into the other, but we have never seen it happen. GW 170817 came close. The gravitational wave signal ended at the moment of merger. The gamma rays arrived 2 seconds later. Everything in between is inference. Was the remnant a neutron star when the gamma rays were produced? Or had it already collapsed into a black hole? The data do not tell you. The models say both are possible. To settle it, you need the post-merger gravitational wave signal. You need to detect the oscillations of the hypermassive neutron star if it existed. Or you need to confirm that no such signal is present, which would tell you the collapse was immediate or the signal was too weak to detect. Either way, you learn something. The next generation of detectors will have the sensitivity to do this, and when they do, the missing link will stop being missing. The transition from neutron star to black hole will be observable. We will see it happen. Not once, but many times, across a range of masses and spins and equations of state. And from those observations, the picture will come into focus. The same applies to the R process. The 2017 Kilonova confirmed that the process is real and that it happens in neutron star mergers, but the details are still fuzzy. The models can explain the overall light curve, but they struggle with the fine structure, the early blue peak, the late red tail, the spectral features, faint as they are. Every piece of data is a constraint, and every constraint tightens the models. But you need more than one event. You need a sample. Dozens of Kilonova observed in detail with spectroscopy and photometry across multiple wavelengths. From that sample, patterns will emerge. Correlations between the kilonova properties and the properties of the merging stars. Once you have those correlations, you can start to make predictions. You can say, if the neutron stars have this mass ratio and this spin, the kilonova will look like this. And then you can test those predictions with new observations. That feedback loop, observation to model, to prediction to observation, is how science works. It is slow. It is painstaking, but it is effective, and it is happening now, in real time, as gravitational wave detectors and optical telescopes work together to collect the data that will define the field for the next generation. Then there is the broader context. Neutron star mergers are one piece of a much larger puzzle. How do galaxies evolve? How do they accumulate heavy elements? How do those heavy elements get distributed through the galaxy, and how do they end up in planets and eventually in living things? The answer involves stars, supernova, neutron star mergers, black hole growth, gas flows, star formation, and a dozen other processes that interact in complicated ways over billions of years. Neutron star mergers are the source of the heaviest elements, but those elements do not stay where they are made. They mix with the surrounding gas. They get incorporated into new stars. They get locked up in planets. They get blown out of galaxies by supernova-driven winds. Tracking all of that requires simulations, models that follow the evolution of a galaxy from the early universe to the present day, including all the relevant physics. Those simulations are getting better, and the observations from gravitational wave astronomy are feeding into them, providing constraints on the merger rate, the heavy element yield per event, and the way the ejector interacts with the surrounding gas. The result is a richer, more detailed picture of galactic chemical evolution. And at the center of that picture, producing the gold, is the collision of two dead stars. The future of the field is bright. The detectors are improving. The samples are growing. The coordination between different branches of astronomy is tighter than ever. And the questions, the big ones, are starting to come into focus. What happens in the seconds after a neutron-star merger? How does the R process work in detail? How diverse are the events, and what drives that diversity? How common are neutron-star mergers in the history of the universe, and how much have they contributed to the heavy element budget? These are the questions that will define the next decade of research. And the answers are coming. Not all at once, not neatly, but they are coming, one detection at a time, one kilonova at a time, one gravitational wave signal at a time. The universe is loud if you know how to listen, and we are learning. We are building better ears, better eyes, better tools for translating the signals into understanding. The 2017 event was the beginning, not the end. It proved that multi-messenger astronomy works. It showed that gravitational waves and light together tell a richer story than either alone. And it opened a door that leads, eventually, to a complete picture of some of the most extreme events in the cosmos. Neutron stars colliding at close to the speed of light, jets launching, gold forming, black holes being born. The whole violent, beautiful, productive process that turns dead stars into the raw materials for everything that comes next, including us. We are, in a very real sense, the products of that process. Star stuff and kilonova remnants, mixed together, forged in violence, scattered across space, and eventually assembled into something that can look back at the universe and ask how it all happened. The answer is written in gravitational waves and light, and we are learning to read it. So here we are, standing on a planet made partly of neutron star debris, holding pieces of gold that were forged in collisions so violent they shook spacetime itself. The ring on your finger, the metal in your phone, the uranium sitting in a reactor somewhere generating electricity, all of it carries a history that stretches back billions of years. And that history is not metaphorical, it is atomic, literal. Every heavy element on Earth was made in the death of stars, and the heaviest ones, the gold and platinum and uranium, were made in the chaos of neutron-star mergers. Events that happen once every few tens of thousands of years per galaxy, scattered across billions of galaxies, running for more than 10 billion years. Add it all up and you get the periodic table, the universe's inventory, built one collision at a time. The 2017 detection was humanity's first clear look at this process in action. Gravitational waves announced the collision. Gamma rays confirmed the jet. The kilonova revealed the gold. And every telescope that could point at that patch of sky saw a piece of the story. It was not just a discovery, it was a demonstration. Proof that the universe speaks in multiple languages and that if you listen to all of them at once, the story becomes complete. We are still learning how to listen. The detectors are improving, the samples are growing, and every new detection sharpens the picture. What happens to the remnant? How the R process runs in detail. How often these events occur, and how much they have shaped the chemical evolution of galaxies. The answers are coming, but the deeper truth is simpler. You are made of this. The atoms in your body, the iron in your blood, the calcium in your bones, the iodine in your thyroid, were forged inside stars. And the heaviest elements, the ones that required the most extreme conditions the universe allows, were made when two dead stars collided at 99.9% the speed of light and tore each other apart. That collision happened billions of years ago. The debris drifted through space, mixed with gas from other explosions, and eventually became part of the